Yeah, you?
Yeah. Fine.
Yeah. For the main speakers?
Main speaker volume.
Yeah, is the main speaker turned on?
Yeah.
In the room, I mean, like.
Yeah.
Really?
Yeah.
But try mic, we can't hear anything.
Oh, now we can.
Oh,
sorry.
what did you change?
뷰티프로다.
Yeah.
Can we use the?
아무거나 돼.
Okay. Test check 1 2 1 2 testing. Could we turn it bump a little? Yeah. Thank you. Testing 1 2 1 2 1 2 testing check 1 2 test quiet. Yep. Okay.
Two.
Yes, thank you. Test check 1 2 1 2 test check 1 2 1 2 testing. Yeah. Check 1 2 1 2. Okay. Yeah, that's good.
Maybe a little bit down.
Yeah, I would.
Softer.
Yeah.
Yeah. Okay.
And the last?
Test check 1 2 1 2 testing check 1 2 1 2 1 2 1 2 1 2 1 2 1 2 test check 1 2 test check 1 2 1 2 testing.
테스팅 하나 둘.
Yes, perfect. Should we start? Yeah. Okay. Hi, good morning, everyone. Hey, thank you again for coming today. I'm Aviral, and I'm a professor of computer science at ASU, Arizona State University. And it's my pleasure to welcome our keynote speaker today, Professor Reinhard van Haxleden. Okay. It's a bit complicated, but doable. Yeah, we all struggle. My name, yeah, I won't even start. Okay, so Professor Reinhardt completed his bachelor's in CS plus physics, my favorite combination. So that is my dream if I would have a chance to do that. Then he did his master's at Penn State and his PhD at Rice University with Professor Ken Kennedy. Then he started working in Daimler in Berlin and Airbus in Toulouse and Hamburg. And then this was last century. And then by the end of the century, he said, okay, enough is enough. I am going into academia. So then he joined Kiel University. Then he's a professor, full professor there. He's actually department chair there. He's been there for some time. And he collaborates a lot with Berkeley, Auckland, I'm assuming Partha, and some other people, and in ENS, right? This is in Paris. Yeah, ENS and INRIA. So he's a very well-known figure in the synchronous data flow computing, and so this all properties and timings of time-sensitive languages and application development. So, Professor Reinhardt.
Thanks, everyone. Yeah, that sounds good. Okay, thanks everyone for the kind introduction, and thanks for having me. So yeah, synchronous community. So somehow 12 years seems like a good time to reflect back on things. So some of you may know this paper by Ben Benist et al. On synchronous languages 12 years later, which I think I have read at least 12 times. And so now let's see, on Statecharts, thanks for the opportunity to reflect on two things. Sequential constructiveness on the one hand, which is the semantic side, and I think that is what I will probably reflect on mostly about. And then also text-first modeling, that is more on the syntactic side, but something that I feel nonetheless is something that is characteristic for this language and which maybe has had even more uptake than the sequential constructiveness. Sequential constructiveness, that's more for, let's say, for the insight, for the semantics crowd. So that's for us, I would say. But text first, that is by no means specific to synchronous programming, but it's in general, I would say, for systems development. So reactive systems, to start at the beginning, they do some computation, they take some inputs, they produce some outputs, and in between they pause for a tiny moment. So that's the synchronous model of computation. Basically that the computation itself should take no time at all, and that all the time that is taken is just taken between the different reactions. So morally, this pause statement should really correspond to some physical time, even if it's just a nanosecond. The pause statement should reflect physical time. And that is actually one thing that has not been quite true at the beginning, at the origins of synchronous programming, because there were some scheduling constraints because of the fixed point semantics. I will get into that in a moment later. That has led to the abuse of the pause statement to have it also inside the computation. And that's one of the things that we wanted to get rid of when we started with the sequentially constructive model of computation, that there is no need for these artificial pause statements within the computation, that they really are reserved for physical time. So that's part of the idea. So the origins of Statecharts, they go back on the one hand to Statecharts from David Harrell, and they also go back to a conversation that we had now about 12 years ago with National Instruments. So they are this all visual company. So you may have known, you may know already their LabVIEW product, so everything is graphical, and they wanted to develop some language with Statecharts like syntax for hardware design. And they had heard good things about the synchronous paradigm. They wanted something with a solid semantics foundation. So they asked us, well, can you come up with a Statecharts-like language for hardware design? And we said, okay, well, let's have a look at that. And so Statecharts, that was the setting. We wanted to have some Statecharts-like syntax. And so here you see David Harrell's original Citizen wristwatch that he used to explain the workings of Statecharts in his original paper. And here you see the foundations. On the one hand, you have these finite state machines. You have these automata here. You have them composed in parallel. So you have concurrency separated here by this dashed line. And you also have hierarchy. So you can have preemption. So in a nutshell, Statecharts are automata plus concurrency plus preemption. So that's what we wanted to preserve. And actually, David had this great idea, but he had some hard time to get it published. So he has a very nice account of getting one rejection after the other. And people thought, well, Statecharts is this visual thing, and we want something solid, and solid has to be text and so on. So it took a while to get the first Statechart paper out, but then he got it out, and then people thought, well, this is a great thing. And there are these Harrell Statecharts, but there are also other things that we can do with this Statechart language. And there was this big debate, well, what's the right language, what's the right semantics for it? And so then in 1994, there was actually Michael van der Beek who thought, well, this is also disorganized, and let's give some order into the chaos. And so he came up with this paper that compared all the, at that point, 21 different variants of Statecharts that you had at this point. So each column corresponds to one Statechart dialect. And he compared it according to different criteria. So for example, whether they would be graphical, whether they would allow negated trigger events, whether they allow timeout events. So there were these different categories, and actually the list goes on much longer than that. So the whole table looks like this. So it gives you an idea that there's quite a bit of semantic variation of Statecharts. And then David saw that paper and said, well, this is all nice and well, but actually you got it all wrong. And my semantics is actually something different. And he came up with a 22nd column where he explained, well, what exactly is what are the different characteristics of his language. And that actually motivated him to really write up precisely what is the semantics of this Statechart dialect. So 1994, already 22 different variants, and we are not even talking about UML Statecharts or Stateflow as part of Simulink and all these others, and Statecharts, of course, are not on there. So the bottom line, many different variations, but the same idea. You always have automata, and you have concurrency, and you have preemption. So back then, there was also the Synchronous community that started to come around with languages like Estera and Lustre and Signal. And Florence Maraninci also saw these Statecharts and came up with a Synchronous Statechart dialect. So the idea of synchrony is basically that you have deterministic behavior. So that is something that the original Statecharts, for example, did not have. So you could easily specify Statecharts where it was not clear whether you would take transition A or transition B. And for example, in the original StateMate tool that came along with Statecharts, there during simulation you were asked, well, do you want to take transition A or do you want to take transition B? And if you synthesize code, well, it was up to the code generator to just generate something. And so in synchronous programming, the idea was from the beginning to have a deterministic semantics, and if there are any uncertainties, then it's up to the compiler to determine that there are any uncertainties and to reject the program if there are any uncertainties. So that's the big change that came around with the synchronous paradigm and with this first Argos language. And there was a further development of a synchronous state chart dialect into Syncharts. So Charles-André came up with this language that was commercially then also known as safe state machines, when Asteroid Technologies marketed that as a language. And here you already see the basic characteristics that you also find in Statecharts. So for example, you have this strong abortion, which is here indicated with this circle at the beginning, which at some point has turned red. So now you have a red circle to show a strong abortion. You have a weak abortion. So the basic difference is basically that you that you either allow the internal behavior to still execute, so to still execute a last wish, that is weak abortion, and in strong abortion you don't do that. And so that is again one of these things where we want to have a deterministic semantics, and where we do not want to have a race condition between, on the one hand, internal behavior, and on the other hand, the preemption. So the semantics clearly says which way to resolve that race condition. Either the inner behavior wins and still gets to execute, or the outer behavior wins that you do the preemption first. And you also have a normal termination, so-called normal termination. That just means when the inside threads, they all have terminated, then you take this transition here. Okay, so that was the setting when we were asked from NI to come up with a good semantics for a hardware-oriented state chart language. And one of the limitations they wanted to circumvent is that the semantics, the classical synchronous semantics, is rather restrictive. So for example, if you look at this little example, you have an initial state here shown with this bold outline, and from this initial state you take a transition if some variable x, some boolean, is not true, just using the standard syntax here that we know from C, for example. And if we take this transition, then actually we set x to true as part of the process. So this is totally normal behavior. So the moral equivalent in a C program, for example, would say if not x, so if something is not done yet, then do something and then record it by setting x to true. So perfectly fine. There is no race condition here. There is no concurrency. Everything clean and dandy. However, it's not allowed in Syncharts or in SRL or any of these other languages. Why is it not allowed? Well, we do not have a fixed point here. X is true and false within the same tick. So remember, in synchronous programming, the computations don't take any time, and here at the same time you would have x true and false at the same time. And if you come from hardware design, this is totally natural. A wire cannot be high and low at the same tick. But if you come from software design, this is a rather annoying restriction, because again, there is no race condition. And so that was the idea of sequential constructiveness, to really take this clear scheduling information that you have here. Of course, you first test the condition before you actually execute this then branch, to really take this information for scheduling to give a clear semantics. So we wanted to preserve the nice properties of synchronous programming, that we have deterministic behavior, that we want to have static checking, so no runtime surprises, and we wanted to have efficient synthesis. However, we wanted to reduce the pain. So just as I outlined it earlier, we want to make it easy to adapt, especially if you are socialized as a programmer and not as a hardware designer. And we want to reject only models where really determinism is compromised. And so the approach is to harness scheduling information from the sequential or imperative constructs. So that's the bottom line. So we thought back then, and that was actually, I think, at a meeting in Bamberg with Parther and Michael Mendler, that we came up with this basic idea. And we thought, well, this problem solved, easy enough, but actually it only started then. So it turns out to be not all that easy to really pinpoint it precisely, and we find it to still be a rich research topic. But so now the language, before I explain a little closer what the C model of computation is about, So first of all, to get an overview, so here's the hello world of synchronous programming, the ABRO. So we have some interface declaration, we have some initialization, we have a super state, we have concurrent regions, we have initial states shown with this thick outline, we have final states shown with a double outline, we have a delayed transition and a trigger, so that is the non-immediate transition. The immediate transition, they are shown with a dashed line. So that means that as soon as you enter a state, you can possibly take this transition, whereas with a delayed transition, the solid transition, you always have to reside in a state for at least one tick. So that's the main difference. And then we have the strong abort, remember the circle now shown red, and we have the termination transition. So that's the graphical syntax. And now as to the semantics, again, the idea is that the sequential control flow overrides the normal requirement of write before read. So that's part of the fixed point idea, that when you want to read a value, any potential writers to that value have already executed in that tick. So that's why the general rule is write before read. For example, in SRL, you have to, if you emit a signal and you test the presence of a signal, you first have to emit the signal and then you test the presence of a signal. So the idea is that writes now are visible only to reads that are either sequentially downstream or that are concurrent. So that means that writes are not visible to something that is sequentially before. So that's why we could write in the then branch something that was read before. So that is the one important change that we do here. So that is one thing. And then we go a little further by wanting to allow two different writes. And here we pick up on a concept that is well established already in SRL, the concept of a combine operation. So the basic idea is that under some circumstances we want to allow concurrent writes. So usually we just want to allow one writer so that we have a unique value. But in some cases when these writes are confluent, then we want to allow them. And so here, for example, if we have some write command that says, well, increment x by 5, and the other write command that says increment x by 3, then these two writes are confluent. And that is something that has been well established already in the SRL language with this combine operation. So if we specify some output signal x of type integer, then we say, well, you can resolve that if you have concurrent writes with this addition operation. And then, of course, if you have two increment by 5 and increment by 3, then combined they will add 8, no matter in which way you schedule these. So the usual way that you specify that in SRL is to say that such a combine function has to be commutative and associative. We do it in a slightly different, slightly generalized way by saying, well, we have a combination function if we have a function that takes two operators, and if it does not make a difference in which way we add two other values y1 and y2, whether we first add y1 and then y2, or whether we do it the other way around. So that's the basic point of having confluent operations, that it doesn't matter if you schedule concurrent operations in which order you do so. And so, for example, addition is such a combination function, but subtraction is also a valid combination function, even though it's not commutative. So that's why we use the slightly different definition here. So if it's associative and commutative, then it is a combination function, but not necessarily the other way around. And associativity in itself is also not sufficient and also not necessary. So now we are armed with this concept of a combination function. And based on that, we can now define relative and absolute writes. So here again is the definition of the combination function. And we say that we have an update or relative write if we use such a combination function. And in this case also this E has to be an expression that does not reference X and whose evaluation does not have any side effects. So these are our relative writes. And everything else, all the other writes have to be absolute writes. And in our Statechart compiler, we assume that relative writes that they have this form that we saw earlier, like plus equals or minus equals, that kind of thing. So all the others are initializations or absolute writes. So any write that is not relative. Okay, and based on that, now the sequentially constructive model of computation defines this IUR protocol. So we schedule variable accesses within a reaction. So if we have sequential accesses to a variable, that is unconstrained. But if we have concurrent accesses to X, then we must follow the protocol that says first we do the initialization. Then we can have an arbitrary number of confluent updates, so updates of the same type, so you cannot mix, for example, addition and multiplication, that kind of thing. And then an arbitrary number of reads. So in each tick, for each variable, for each set of concurrent accesses to a variable, we want to follow this schedule. That's the protocol that we have to follow. And I have the feeling that the mic just, is it still working? Yeah, okay, it's maybe a glitch there. Okay, so far so good. So now we can accept many more models, like the one that I showed at the very beginning. But the world, of course, is not perfect. So in this case, we still have to reject some models. And by the way, here you see now a textual variant and the graphical variant. So this is already a first example of this text-first modeling. More on that later. But the basic idea is that as a modeler, you write this text, and this on the right-hand side is then synthesized automatically. So here we have two regions, regions A and B. And in the first region, well, we set x to 0, and in the second region, we set x to 1. And, well, it's still not clear which value we get for x at the beginning, depending on which way we schedule these. So we still have here a so-called causality cycle, and the compiler rejects the program. And this is another view of the same model here, from the same text. We here have a different synthesis that makes this more explicit. It shows the data flow, that here we have two writers to the variable x. So this is the so-called induced data flow. So one of the things that I really like, that with just this one click, you can already get a kind of data flow diagram that tells you which way the data flow, rather than just having this hidden broadcast that you typically have in Statecharts. So here's another example. So here we say, well, if we don't have x, then we set y to true. And here, if we don't have y, then we set x to true. Well, of course, it depends on which way in which order you do things. What result you get, non-deterministic, and again, the compiler rejects it. And here you see another view of the internal workings. This, on the one hand, on the left hand, you see this compile chain. So each of these boxes is for one version of our little program, and we can click on these boxes, and then we see these different versions that we have. And here at the end, we have the version of the so-called SC graph, or SCG in short. And we will get into that in a moment. But the interesting thing here is that here you see this cyclic dependency of the data flow and of the control flow that tells you that actually here you have a causality cycle. So that's the information that you see as a modeler. Not only that there is a problem, but also it is indicating where the problem is. Okay, and a variation on the example. Here you see we don't test the negation of x, but just x itself and y. And in this case, one might argue, well, x and y are false originally anyway, and so we do not speculatively execute anything. We only execute it if it's really, if the trigger is fulfilled. And here, if none of the triggers are fulfilled at the beginning, then we don't have any race condition here. But it still gets rejected because we have a static analysis. So we do not test whether we potentially might execute something, but here the compiler statically tests whether there is a possible data dependency, and therefore it rejects it. Okay, so now we defined the IUR protocol, and now the question is, well, when is a program, when is an SC chart sequentially constructive? Okay, and so we now defined it to be sequentially constructive if for all possible inputs there exist runs, executions, that obey this initialize update read protocol. So we also say that it's reactive. And furthermore, if all these runs lead to the same result, so they are deterministic. And now one unfortunate fact here is that we have such a second requirement. So to be honest, when we set out to come up with this definition, Michael and I, we sat down for days and weeks, and we really tried hard to come up with a definition where you really had just this constructive concept, this constructive nature, that if you have a run, then it provides you a unique result. But unfortunately, there are counterexamples where you can have different runs. They all obey this initialize, update, read protocol, but they still lead to different results. And so, in a way, this really is less constructive, we have to admit, than SRL's constructive semantics, because in SRL, if it's constructive, it really means that you have a proof that you can come up with one execution that obeys the constructive requirements. And here we don't have that, so that is a weakness. But I will come back to that. But so this is now, in the current definition, that is a problem. Or I think it's a problem, or let's not say it's a problem, it's not nice. In practice, however, we say, well, we already have this analysis done statically anyway, so we have this static criterion. So here we say that it's acyclic, sequentially constructive, and there we do not have to worry about this definition up here anyway. So there again we have a very clean conservative concept. So in practice, in reality, this is not an issue, but it's still, deep inside it's still nagging me. So that's why I'm mentioning it. Okay, but in practice, don't worry about it. It's a rather straightforward static criterion like you have in other synchronous compilers as well. Okay, so now let's look a little closer into the inner workings. So one thing that we wanted to have is we wanted to have a very small concept or a very small set of core constructs. Like in SRL, for example, I think part of the beauty of SRL is that you have this very small core language, and once you have clearly defined the semantics of this core language, then you have defined the whole rest of the language, and all the rest is just syntactic sugar. And we wanted to follow the same approach, and it turned out that actually just 5 elements are sufficient to capture everything that you need for Statecharts and for other sequentially constructive languages. So what are these 5 concepts? Well, we have regions with an initial state and a final state, or threads of control. We have triggers. So we either, if a condition C holds, we take the first transition, or if it doesn't hold, we take the second transition. And now remember, these are dashed lines, and the dashed lines were immediate transitions, which you could take immediately as soon as you entered something. So the same thing with the effect, that is an immediate transition that just does a certain assignment. We have superstates that bring concurrency into the game, and we have states. And this is where we actually don't have a dashed line, but a solid line. So that means in a state, you really have to reside for at least one tick. Okay, so these are the 5 building blocks of Statecharts. And we map them to lower level constructs, namely the sequentially constructive language, SCL, and the sequentially constructive graph, SCG. So remember the SCG we saw already earlier when I showed the cyclic dependency, that was an SCG. And so these concepts map one-to-one. The region becomes such a thread with an entry and an exit node. The trigger becomes a conditional. The effect just becomes an assignment node like this. The superstate becomes concurrency with fork and join. And the state becomes a pause node or a delay node. So a delay is basically like a stop sign that is cut in half. And the first part of the stop sign is the surface, and the second part of the stop sign is the depth of the pause statement. So if that rings a bell because you are already in the synchronous world, then good for you. If it doesn't ring a bell, don't worry. It's just surface is the beginning, depth is the end of it. And actually years later, it got pointed out to me, well, here you actually have just put it the other way around. Now, where actually time passes, here you have a dashed or pointed to be precise, and where time doesn't pass, there you have solid lines, which is just the opposite from here. And, well, what can I say? Yes, it's just the opposite. It just worked out that way. So in case you're wondering, yes, that's the way it is. So down here, solid lines are the default, and up here, dashed lines are the default. Okay, so just keep in mind here we have the pause node consisting of this cut in half stop sign. And the nice thing, if you do it this way, is that you can move the surface and depth nodes around arbitrarily. It doesn't have to be stick in one place, and we will see an example of that later. So now, one example, the little ABO, if it gets transformed into SCG, we see it over here. And now maybe a little closer, we see here, for example, these initial assignments to O1 and O2 up here. Then the fork join, we have two concurrent threads which correspond to these two different regions. And here, for example, in this one region, we test for A, just like down there. If A is true, then we take this transition, then we execute this stuff. If not, then we pause. And here we see this cut in half stop sign put apart or torn apart, so where the surface is down here, the one part of the pause statement, and the depth is up here, the other part of the pause statement. And so this allows you to arrange this SCG, which is also done automatically, in such a way that the control flow within the tick is always going pretty much from top to bottom. And if you have control flow that always goes from top to bottom, that already gives you a good visual indication that things are all right, that you do not have any causality cycles. And so that's why we like this way, this presentation, that we always have this top to bottom, and that's why it's nice to be able to take these tick boundaries apart from the beginning and the end. Okay. By the way, this would be an excellent point to ask any questions, just in case you have any. So I'm happy to have it a bit interactive. So I have enough material to cover us, but I promise at 10 after 10 I shut up no matter how many questions you ask. Not everybody happy so far? Okay, all right. So this is what we looked at now. And now let's also look at the other direction, upstream, while we have the syntactic sugar that I mentioned. So we have the core SC charts that map down to here, and on top of that we have the extended SC charts. So here, for example, we have the different types of preemptions or abortions that all then through different model-to-model transformations get mapped down to these elementary constructs. So if we take stock so far, we have extended SC charts, core SC charts, normalized or core SC charts that I discussed in a little more detail, and then we have the SCL and the SCG. So now we have a fun language, and of course we want to somehow compile this into software or hardware. And so in the original paper we presented two types of compilation. On the one hand, the data flow approach, which is morally quite close to the circuit semantics of STRL, which is also why it's good for generating hardware. And we have the priority approach, which is more software-like. And both of these I'm going to briefly describe in the following. So this is the data flow approach that corresponds to the circuit semantics. And again, we have this one-to-one mapping of the different, of the 5 different constructs we have here. So on the one hand, we have data flow code, equations, and on the other hand, we have these circuits that this translates to. And the basic idea is that control flow is realized as guards that tells us whether a piece of the program is actually executing if the guard is true, or if it's not executing, if the guard is false. So maybe to begin with the conditional. So we have the guard that tells us whether the condition is executed at all. So all the incoming guards, they are all together here. And then we have a guard for the true branch, which is true if the condition is executed at all and if the condition holds. And we have the guard for the false branch, which is just the opposite of that. And it translates to this straightforward circuit here. The assignment, well, we do this assignment if the guard is true, and X gets either the value E, the new value, if the guard holds, or it gets the old value, X. And this already may ring a bell with you, x prime and x. Well, this is basically just static single assignment. We have two different incarnations of the same variable. And that is actually one, I think, good way, legit way to think about sequential constructiveness. It's basically doing SSA for you, that it allows you to just reuse the same variable, and the compiler splits it up into all these different incarnations that you would have with SSA. And that also manifests itself here in this circuit semantics. Then for concurrency, well, if you know the circuit semantics from SRL, then you might realize these done and empty flags and the synchronizer. Again, if you don't recognize it, don't worry, but yeah, let's not spend too much time on it. But the one last interesting thing, I think, is the pause statement, which basically corresponds to a register. Because the pause statement is where you actually have to remember something, where you have to remember where control flow stayed from one tick to the next. So that's the only statement that generates state registers for you. All the others are just combinational circuits. Okay, so much for the data flow approach. And that is a quite robust approach. However, the only disadvantage of that is that because hardware, you cannot reuse the same hardware multiple times within the same tick. That's why it basically macro expands everything. If you reuse something many times, that leads to rather large code. So I will come back to that in a moment. But now let's switch to the priority-based compilation. Remember the second column, the more software-like approach. So here we don't simulate the control flow with guards and for basic blocks, but again with program counters and threads. So we do a thread dispatching based on priorities. So if you have data dependencies, if you have a concurrent writer and a concurrent reader, the concurrent writer must get the higher priority than the concurrent reader. So the idea is that in each tick, you always execute the highest active thread and then the next highest priority active thread, and so on, until you have executed all the active threads. And that leads to a slight extension of the SCL language, namely SCLP, which is SCL plus priorities, or more precisely, prio IDs, which fold the priority of a thread and a thread ID into one, so that we get unique prio IDs. Because multiple threads can have the same priority, and to keep them apart, we add a thread ID to that. So in C, we implemented that as macros using computed gotos. I will get to that. So for me, that is one of the nicest things of code generation, these C macros. And maybe it's just because I'm a C nerd, but well, maybe some of you will appreciate it too when you see it. In Java, unfortunately, no macros, no gotos, so the Java code gets a lot uglier than the C code. The C code, I think, is really rather elegant. So here for the example that we saw earlier, we annotate this SCG with priorities based on data dependencies. So here, for example, we have a writer to be before a reader to be, and so that's why, if you can't read it, don't worry, I can't read it either, but trust me, this has a higher priority than this here. And we have this prio ID, which then gives unique prio IDs, so at runtime you can keep things apart. And now, the macros. Okay, so maybe first on the top right here, we have an SC chart that actually indicates the different execution states of a thread. So each thread can be either disabled, or if we fork off the thread, it becomes enabled. And an enabled thread is either actively executing, or when it's pausing, it's inactive. And then at the next tick, it becomes active again. So the bottom line is that for each thread, you have to keep track of two things, whether it's enabled or not, and whether it's active or not. And now let's have a look, a somewhat superficial look. So in class, I really like to spend at least half an hour on this alone, but now just a couple of minutes should do. So first we get a Boolean type. Then we have something, one of the nice things that a preprocessor can do for you. It can generate automatically a label that you can go to based on the current line number in the source code. So each line in the source code can give you a label, and this is some helper stuff. We will see this in action in a moment. And then down here we just have a little bit vector manipulation stuff to keep track of these two things, whether the thread is enabled or not and whether it's active or not. So let's not worry about that too much. Then, as I said, in the priority-based approach, we keep track of program counters. And now, of course, as a programmer, it's a little difficult to access the program counter. Usually in C or Java, if you just ask for the program counter, well, it's an address and I don't get that. But we can still do so at a somewhat higher level. And so that's what this set program counter macro does. It's, so we have an array of program counters, one for each prio ID. And here we set a program counter to the address of a label. Remember, we automatically generate labels, and GCC allows you to take the address of a label. So that really translates to a program address, so something that a program counter will actually go through when you execute a program. And then we have a pause statement. So you may wonder, a pause statement in C, how can you do that? Well, here it is. Well, the pause statement, it calls this little helper function, and this helper function, well, it sets the program counter to a label, and that is this automatically generated label, which is just after the pause statement. So it basically says, well, here at this point, you don't execute any further because you go to this something, but next time when you start the tick, then you start right here, right after the pause statement. You start right at that label, and that's the pause statement. Then we have fork and join, which basically starts a new thread, but let's not get into the details of that. The parallel statement basically just says, well, the thread that reaches the parallel statement is finished now, go somewhere else. And here is a macro that allows you to change the priority. So let's not look into the macro, but the thing is that the thread can change priority within the tick, and that allows you to do back and forth scheduling. If you have complicated dependencies within a tick, then you can resolve these by allowing a thread to assume multiple different priorities within the same tick. Okay, so now, what does a program look like for this SCG? Well, it looks like this, using the different macros that we have. So here at the beginning of the tick, so this is the whole tick function, we have some tick start macro. Let's not worry about that for a moment. Then we do these assignments. Then we fork off the same thread, the first thread. So this is the first thread. Then we have parallel to the second thread. We join it, and then some assignments again, and then that's the end of the tick function. And in between, for example, we have these pause statements. So what we see on the right-hand side is a C program. It may not look like a C program, but it is a C program just using these macros that we designed earlier. So we just can use GCC and compile this thing, and it does the right thing, a concurrent C program. And now let's look a little bit into how these macros expand. So here we have the first half that we saw in its expanded version. So here, for example, if we look at the pause statement at line 94, that translates to the program counter of the current thread ID, CID, gets the address of this label, and then we finish the current tick by go to this thing, and here we have the label. So that means the next time we start the tick, then control starts right here at this label. That's it. And let's look at the second half. So the one last juicy bit that I want to share with you is here at the end, because remember, the execution works this way that always we execute the thread that is the highest active thread. So from all the active threads, we take the one with the highest prio ID, and we want to dispatch that. And we store the information of the active threads in these bit vectors. So the task is that from a bit vector of active threads, you have to find the leftmost one, basically. You have to find the highest prio ID. And now, of course, it's a straightforward exercise to write a little C loop that does that thing for you. but still it's a loop, and you have to go through the whole thing and many iterations and so on. But if you're lucky and you're using GCC and you're using an x86 architecture, there is this one assembler instruction, namely bit scan reverse, that does just that. It takes an integer, 32 or 64-bit, finds the index of the highest one, and returns that. And now, with this one assembler instruction, you know which thread to execute. And there you now look into this array of program counters, and you use this index, the current thread ID, to just jump there. So it's basically two assembler instructions. The one bit scan reverse, and the other one is this computed goto that does the dispatching. And so I challenge you to find a faster dispatcher than that. So I think this is really rather efficient, and I just love it. Okay, so take-home message, in case you haven't noticed. You can do wonderful things with the C preprocessor, we can do wonderful things with computed gotos, and we can do wonderful things with embedded assembler. So I'm not sure how often we still teach these things, but I think you should really know about it, and it's really cute. So, classroom tested. So here, for example, there's a big model railway that we use, and where we also tell the students to eat our dog food and use Statecharts, and so a controller, rather complex controller. So originally it has 10,000 Statechart nodes, so that's before expansion, before normalization, and so it turns out to be pretty big. So remember, I said that's one disadvantage of this netlist-based approach. It gets pretty big. That's why we also have this other approach. So compile time, 2 minutes, not the greatest, but it's still okay, I think, considering that you have 650,000 lines of code, and the reaction time is pretty good, 2 milliseconds. So huge code, but it's fast, and it works. So much for the sequentially constructive basics, and it's also used in other languages. So for example, the Blech language, which I think is quite nice from the folks at Blech, and there are also other languages, but often they don't call it that way, which I think is fine, because it's just a very natural way of programming, I think, the sequential constructiveness. You do it all the time, it's just not so common in the synchronous world. Okay, so on that, a small number of core constructs are sufficient to really build everything that you need for a reactive control flow. And on top of that, you can have, of course, lots of syntactic sugar. So the nice thing is that we can keep the core semantics clean and simple, and we can easily adapt it to different syntheses. But the resulting code is difficult to map to the original model. So Statecharts, they are also used now in industry for describing railway interlocking systems, and they have fairly harsh requirements on the validation of the code, and part of that is that the generated code must map back to the original model. And that has actually motivated a different approach, which we call the interpreter approach, which basically tries to generate code which is quite close to the original Statechart, and then gets compiled just using your usual Java or C compiler. So there, in a way, we call it interpreter because it's so close to the original model of the generated code, and that is something that is used now, but I would still like to work on it a little further. So this is something that I would say is still an active project. Okay. So much for sequential constructiveness and the beauty of that. And now let's, as I promised, go a little bit into the text first side. So Statecharts have been textual and graphical from the beginning, and in the Keeler tool that we use for our ecosystem, the modeler writes textually here, and then the different graphical views are synthesized automatically. And that it's automatically done also has the advantage that you can do different views. You can also have more abstract views or more concrete views without having to redo it yourself, because it's all done automatically. And we use this automatic layout from the Eclipse layout kernel, or ALK. And now taking a step back, so why are we doing this? Well, we call it pragmatics-aware modeling. So Somehow that term doesn't seem to be all that popular, but I haven't found a better term yet. So it's basically borrowed from linguistics, where the field of semiotics is divided into syntax, semantics, and pragmatics. So pragmatics basically telling you in which way you should use different language constructs. And so here we basically want to use textual syntax and graphical syntax as effectively as possible. So the idea is that we want to free the user of tedious mechanical work, such as manually placing objects or manually navigating in complex code. And so I don't know about you, but sometimes something that I hear time and again, people saying, well, graphical, all nice and well, but I prefer to type. It's just faster. And I think many people feel that way. And if you're using a traditional, what you see is what you get, graphical editor, then I don't blame you for that. And so we really hope to get also you, if you prefer textual, to think about maybe to generate graphics along the way. You can still type, all nice, but generate graphics along the way. So the idea of pragmatics is that we want to explore new interaction methodologies, new analysis, and new ways to synthesize models. And the experimental platform, I already mentioned, Keeler, so Keel Integrated Environment for Layout. That was the Keel tool, and at some point we moved on to Eclipse, and so we tagged on an Eclipse-rich client. So that's why now we have Keeler in that, and the Eclipse layout kernel. But the Eclipse layout kernel is basically just a Java library, so you don't have to use it in Eclipse. So, for example, the Ptolemy tool also uses Elk, even though Ptolemy is not running on Eclipse, but it's in Java, and so that's why it's also using Elk. And the key idea here is that we want to use the model view controller paradigm, which is probably familiar to you already from software engineering, used in a different way. But if we go back to scripture, what Trygve wrote back then, well, a model represents knowledge, could be a single object, or it could be some structure of objects. A view is a visual representation of the model, would ordinarily highlight certain attributes of the model and suppress others. It's just acting as a presentation filter, so different views. And a controller, that is the link between the user and the system, and it provides the user with input by arranging for relevant views to present themselves in appropriate places on the screen. So I don't know whether Trygve thought of automatic layout when he wrote that, but I'm certainly thinking of automatic layout when I'm reading that, because that's exactly what we want to do. That we want to automatically arrange different things on the screen to reflect your model. And so that's why this distinction between the model and the view works very well for us. And you can think of the model as the textual description, even though, of course, the textual description is also nothing else than a view. But if you write a model, then you write it in text, and the view is generated automatically for you by the controller, the automatic layout that brings it all together. And so actually sequential constructiveness, yeah, nice and well, and some languages are using it, and I think it works great and so on, but it's rather a niche thing, to be honest, I think, like maybe, but pragmatics, that really seems to be something that people find useful in many different ways. So this, for example, is a nice email I got from somebody, Bosch Siemens Hausgeräte, so they are doing dishwashers and so on. So they also use textual modeling for productivity, but they also want to have graphical views, and that's why they use our infrastructure. And just yesterday I looked at some statistics for Elk.js, which is the JavaScript version, the transpiled version automatically from Java, and well, about 2,100 stars. And for me, that is a very meaningful metric. That means 2,100 people, they downloaded our stuff, and they took the effort to click on it and say, I liked it. So I think that is really, for me at least, as interesting as citation counts. Citation counts are of course also interesting, but I think this is really a very nice feedback for the whole team here. And well, there are quite a few repositories depending on it, which is also, I guess, on the one hand flattering, but on the other hand thinking that maybe there's just 2 or 3, or at the best of times 4 graded students maintaining all this, and there are all these many repositories depending on it. Slightly scary thought. Usually we don't hear too much from it, but if our server is down for more than 12 hours, then emails keep coming in and the forum is filling up and so on. So people are really paying attention to this. So another language that also is following this text-first approach, for example, is lingua franca, which we are very happy to be part of. So it's really a great team that Adli put together there. And so they have also been following that. Here we see a little example of a text and the graphics synthesized from that. So yeah, text first. If you are coming up with a new language, a new way of doing things, then I recommend that you may have a look at this text first. So a couple of minutes outlook. Model order. So think of this as C chart. So we have two states, state 1 and state 2, and we transition from state 1 to state 2, and we transition from state 2 to state 1. And now take a moment and in your mind play automatic layout and think of how you would arrange this automatically on a screen. Everybody has an automaton? Okay. All right, so this is a view. So here you see the two states with the transitions between the two of them. So, and it's perfect from the graph drawing perspective. There are no edge crossings, it's all evenly spaced and so on. So who of you had this view now in your mind? Don't be shy. Okay, a couple. All right, thank you. So now I have another view. So you may try to spot the difference and then think, who of you had that view in your mind? Well, here it's a bit of a wash, but but I would argue that the right-hand side, well, it depends, of course, in your natural language, whether you write from left to right or whether you write from right to left. But at least here, in my mind, actually, this is the more natural thing. So because it more naturally, it's closer to the mental map that you have here. I mean, it's also, of course, the names, first one, then two, but first you have this thing and then the other thing. But from the graph drawing perspective, this is just as good as this. Any idea why this is just as good as this from a graph drawing perspective? So somebody remembers how a graph is defined? Well, a graph is a pair consisting of a set of vertices and a set of edges. And, well, sets don't have any order. And this is, I think, where the graph drawing community has gotten it really wrong, or the graph community as such, because a graph, I would argue, in the real world, often a graph has order. And so we argue to really replace set by list. And that is what we also refer to as model order. So the basic idea is that you have a mental map that you then preserve this mental map. And that's what the model order does. So take-home message, automatic layout is practical. Users have not to spend precious time on manual layout, and they want to have control over how a diagram looks. And users typically do not love to surprise themselves or to have unstable layouts. And they also want to learn too much about different layout options and so on. Things should just work. And I would say that you should really revise the definition of a graph. And last minute now on sequential constructiveness, I told you, well, there was this nagging thing about not having deterministic results. And here, for example, that this model gets rejected. Well, why not let the order, in this case of regions, also again prescribe the schedule to resolve the race condition by saying, well, first we have the one region, A, and then we schedule region B. And this is already used in many places. So, for example, also in the PLDI language, that is also just doing it that way. So in the synchronous world, this is anathema, but or may not be the first thing that we do that is a bit anathemic, if that is an adjective. And so it's still deterministic, still under programmer control. No more nasty causality issues, simpler semantics. I think it could become a lot simpler. Price to pay, well, no back and forth scheduling within a tick, but, well, I'm not sure whether it's really a big price to pay in practice or not. So wrap up, we have 5 core constructs. We have this model of computation where we relax synchrony. We explore text-first modeling, and still plenty of things to do. And last slide, sequential constructiveness is natural for programmers and proven in practice. So far, it's a bit tricky to formalize precisely, but maybe with this last thing, it could become a lot easier. Should be taking even more advantage of textual order, and it's easy, and so to easily control the scheduling, that is the key. And on text-first modeling, well, it's natural for programmers and proven in practice. It harnesses the power of automatic layout, and we should take even more advantage of the textual order. Remember the model that I mentioned at the end. And easy control of the layout is key. So with that, thanks a lot for your attention. If we want to, we could still have a brief demo, but I could also show it to you later if you're interested in that. Okay, so thank you very much.
Time for questions, or maybe we can watch the demo.
Thank you very much for the nice talk. I had a question about slide 38, roughly.
Slide 3.
This is not the slide, maybe close to that. Maybe there's an overlay or so. It was where you introduced basically the dashed cycles. Maybe 43 is another line where that I remembered. Yeah, this one is good.
Yeah.
So you have basically you connect the surface and the depth.
Uh-huh.
And I presume you want to have a cycle-free graph normally. This is an exception to that.
Well, okay, yeah, this cycle, that doesn't matter because that is at the boundary of a tick. So we don't want any cycles within a tick.
Mm-hmm.
That's the thing.
So it's basically sending information to the next generation or the next instance of this.
Right.
Basically to
and
the
so
future.
That information, right. And so, so this, remember this corresponds to a pause statement that maps to a register. And this register is where we remember a state from one tick to the next.
Mm-hmm. Okay, thank you.
Yeah. Okay, thanks.
Hi, thanks for the talk. There are obvious parallels to be made with what the real-time community has done. Do you have experience working with the real-time community, for example, for this idea of recurrent real-time tasks, periodic ones, or in real-time operating system deployments?
Yeah, so in a way, I think we consider ourselves to be part of the real-time community. And so, yes, you can think of this also as a cyclic executive, where you basically have this idea. So I would say the Synchronous community takes it, is a bit more specific in that, or special, whatever way you want to call it, in that we have the underlying assumption that within a tick, we do not pass any time, so that we have instantaneous computations, and that's why we typically have this fixed point semantics, which is usually not necessarily the case in real-time programming. Yeah, but it is, so this is meant for real-time systems, so like these railway interlocking systems that I mentioned, so that's a typical real-time application. Yeah, that's a
Thanks.
good point.
I mean, in other aspects, the context of this is more about correctness, and the real time is more about schedulability and performance. Oh, any other questions? Time for demo?
Okay, little demo, all right. So let's have fun. So demos are always exciting, so everything can happen during a demo, so let's see. All right, so I just got briefed from my students on this, so, because unfortunately I don't get to do this that often anymore. So. Okay, so I think the one thing that demos, where demos are really different from slides if you want to explore the pragmatics. So if you want to see how things, how you can interact as a modeler. So here, for example, we have a little motor description. And so remember, a view can be very abstract. It can highlight certain attributes. So at this point, we start with a very abstract view that just tells you, well, we have 3 concurrent regions here, one that sets the speeds, one that controls the motor, and one that simulates time. And now we can look inside. And here, for example, then the simulation time, here we see, well, there's one during action that does the different things. And when I click through the diagram here, it automatically navigates the text to the portion that I'm looking at. So here, for example, we have this initial state, sim time state, during which we have this during action, and here we have the during action. And I can also go to a different, I can expand this, for example, the control motor, and if I click on a state, then it moves to the state on the left-hand side where I see all the details. So here, for example, these transitions here are very abstract. I only see the different priorities. But if I want to see more details of that, then here, for example, and the layout, the label management, this is now a very abstract version where I just show the priorities. If I want to show the full labels, then I click on original labels, and then I see that the diagram becomes a lot larger. And that's why it's a good idea to abstract things, but I can do these labels also in a bit more compact, so we call this semantic soft wrapping. And so now things are a bit more compressed again. And yeah, now let me do it the more abstract thing again, so just the priorities. So I can play also with the way the layout is done. So here it's done from left to right. And now let's do it, for example, all vertical. So this is a different layout that I get here. So usually the nicest thing is if we alternate between horizontal and vertical, if you go down the nesting option. So this is the horizontal and vertical thing. And now let's explore the set speeds. And so here, for example, we can play a little with the model order. So let's see, there was one pragma. So here, for example, if I want to add a transition from the acceleration state to the check-min state, I prepared something. So here I have this transition which is commented out. And now I'm going to uncomment the comment. And now watch what's happening to the, so here we have accel and decel and nothing in between. And now I'm going to uncomment it. And now, well, we have this new transition, but what we also notice is that the accel moved down, the accelerate, and the deceleration is up. Remember before it was different. If I comment it again, so it moved around, so it's not stable. That's bad, even though from the graphical perspective it's all equally good. And so now so now the new thing is that we want to consider model order. So here I have this layout directive here, which actually forced it to not do the model order here. This layout directive, consider model order strategy, none. And now if I go to the default behavior, then we consider the model order that first we have state accel and decel, and now it stays that way, no matter whether I have the added transition or not. So I have better stability now. Okay, so that maybe gives you a little idea of what the interaction with this diagram looks like. Okay. All right. Thank you.
Thank you, Professor. Thanks, Leiden. And with this, we close this keynote session. And the next session starts in 20 minutes at 10:30. So please come back in 10 20 minutes. Thank you.
Okay. Thank you again.
close the door, please. So we will start this session. This is embedded systems and real-time optimization. So the first speaker is Yi Xiaoxing. He will talk about Multicore benchmark framework for real-time embedded systems. So we will leave the floor to him. Feel free to start.
Thank you very much. Thank you very much. I'm Xingyi Xiao from Nagoya University and Takayama Laboratory. It's my honor to be here to introduce my research with you. And my topic today is RTES Bench, a multi-core benchmark framework for real-time embedded systems. And then my introduction will be divided into 6 parts. And at the first part, I will introduce you the background of my research. And I will explain you why we think that the multi-core system benchmarking is so important and the challenges when we evaluating them. As we all know, embedded systems with multiple cores have been rapidly introduced to meet the growing performance demands. And in order to understand the behavior of the systems and to evaluate them, performance evaluation methods and tools are very important for ensuring the real-time behavior of the systems. And as long as we know, for single-core systems, there are both well-researched statistical analysis method and benchmarking methods. And they are developed very well. And unfortunately, for the multi-core systems, evaluation methodology are seldom discussed, especially these features that only multi-core systems have. For example, the inter-core interface and any other resource contention may influence the system badly. And the challenge when evaluating this system is that we should perform evaluation methodology for multi-core system evaluating. And by using this methodology, we should establish the scalability of different RTOS across various hardware platforms. And we need a convenient research and a develop tool. So we want to develop not only a methodology to evaluate such systems, but also we want a tool to simplify the work. And here comes to our goals and contributions. Our goal is to design and implement a benchmark framework. Such framework should allow the implementation and continuous update of various benchmarking scenarios. And it also should support a wide range of hardware platform and RTOSes. And it should automatically evaluate a specific target based on user-defined requirements. And so our contribution is design and finish such a proposed benchmark framework. And we implemented a prototype on 3 different systems applying our multi-core benchmark methodology. And through the experiment, we revealed the system performance characteristics, which we defined as the system behavior change under different contention. And we also found some features and bottlenecks through evaluation results. I will introduce this part in the later part. And then I will introduce you the framework design of our framework from 3 perspectives. The first perspective is the module perspective. Our benchmark have 5 modules. The first module is the benchmark scenario module. In this module, we contain scenarios templates that are written in our general interface. And with such interface, we can write the benchmark without any concern about the detail of hardware and RTOS. It's very convenient. And in the RTOS and hardware details module, it contains some hardware information and RTOS information. If you offer some implementation to the interface we offered, you can add new support to the RTOS and hardware without any further work. And also, some compile and execution script should be stored here too. And the third part is the user parameter module. And in this module, benchmark user can offer parameter to decide the target system they want to evaluate, and other parameter like the number of active cores or some test duration or stress step. This parameter can help the generator to generate the C source code automatically. And the fourth part is the executable code generation part. executable code generator is written in Python and take charge of the generation of a executable C source code, and then the C source code can be executed and evaluated automatically. And the final part is the analysis part. In this part, the output of the benchmark can be captured and be outputted with histogram or line chart. And then I will introduce you the user perspective. 3 kinds of users can use our framework to do some job. For example, benchmark user. As a benchmark user, for example, like researchers of benchmark or some engineer who want to select suitable hardware or ATOS. They want to evaluate the system to see whether they fit their application. Then they can use our benchmark to see the performance and the different stress contention and can figure out the feature and the bottleneck of the system. And as a benchmark developer, they always need to test their new developed benchmark scenarios. And then they need a platform to test their benchmark methodologies. Thus, they can use our framework to finish this job rapidly. And then the third user is the system developer. They also can offer some information to the framework and rapidly evaluate new devices or ATOSes. This is the 3 user perspective. And finally, I will introduce you the simple workflow of our benchmark framework. Please pay attention to the red arrows here. And first, the user decide the target system and the other features like the core number or stress step as input parameter. And then the executable code generator locate the platform templates in the scenario module or the detail module, and then generated the C source code with the information offered. And the C source code is then placed to the project routing and executed by a script offered in the ATOS and hardware detail module. Finally, the serial output is captured by the analysis module, and the data is output and in the histogram or line chart form. This is the workflow of our benchmark framework. And then we implement the methodology and the framework design into a prototype. The key point of the prototype is mainly 2 parts. First, the benchmark scenarios we select, and the next one is the target system we selected. And the key benchmark scenario we used in our prototype is just based on our former work in the article below. The main idea is that in order to understand the behavior of multi-core systems, it is essential to evaluate their performance under different contention scenarios, which we think is very, very important in multi-core situations. We treat the ATOS and the hardware as an entirety and test them on API levels. We first group the API by resource access path, just like shown in the left hand. And the access path based on the fact that we can group them on the fact that state-of-art ATOS shared similar API design, so we can group it and targeting them. In this prototype, we target on most commonly used API and group them into 6 patterns. The patterns are shown on the right picture, and we have 6 patterns and selected their typical API. For example, API that get the object information or acquire some semaphores. They are typical API and it can be tested in our framework. And then we designed a workload evaluation and scalability evaluation. The workload evaluation part is from the idea of stress workload evaluation. We place the target API on one core while stress are placed on the other cores. We adjust the frequency of the stress workload APIs to reproduce potential contention scenarios. And the stress is designed within 2 dimensions, just like the picture on the left. And the first is the access target. It is because the difference between task and object accessing can influence the behavior badly, especially in finer grained system. And the shared resource access and the private resource access is the other feature we designed. It's also important because shared resource access may cause badly delay in the overall system. We adjust the ratio of the access to reproduce the contention. This is the workload evaluation part. And to the scalability part, it is just similar. We want to figure out how the overall performance changes while the active cores is increasing from 0 to the maximum. So we add the active core one by one and see how the overall performance changes to do such scalability evaluations. And then is the system detail part. In this part, we selected 3 different systems which contain some representative RTOS and hardwares. For example, in the first system, we selected the NUTIX, which is a POSIX-style RTOS. It is very representative because if we can do some work on this RTOS, and then we can use the methodology to different RTOS, such as Linux or other POSIX-like RTOS. And we select the Sony's presence board. It's a 6-core board, and the system 2 is the FreeRTOS and the X-Core AI. The FreeRTOS is the most widely used open source RTOS in the world, and the X-Core AI have 16 logical cores on 2 physical cores. It is very suitable for our evaluation. And to the system 3, we select the Topaz FMP, which is developed in our laboratory, and it is a special RTOS with fine-grained lock design, which we can see how fine-grained lock design can work in multi-core situations. And we select the Xilinx board with 4 ARM cores in this evaluation. And then I will introduce you some results and interesting points in our experiment. At first, we want to figure out the baseline execution time of the 3 different systems in 6 different patterns. We want to see the performance characteristics, which in other words, the change of the performance of the API under different stress. So we want to see the baseline execution time, and after that, we want to normalize the data with the baseline execution time. So we first figure it out and then do other evaluations. In the benchmark storage workload evaluation, with the stress workload evaluation, we can see the overall performance change under different stress while also find some features and bottlenecks of the RTOS and the hardware devices. The picture on the left shows the overall performance with the parallel stress workload. And the picture on the right just figures the FMP situation when the resource access is contentional. Let me raise some examples of the interesting points in our experiment. Please see the green line here. It shows the benefit of fine-grained lock design in multi-core situations. It works very well when the resource access is parallelized. And another interesting point is that we can see the orange line. It represents the behavior of FreeRTOS on X-Core AI. We can see the behavior do not change after we increase the cores from 7 to 14. This is just because the design of the hardware is based on 2 physical cores, and the cores do not interfere each other. This fact shows that our benchmark framework and our methodology can have the capability to understand some feature and the bottleneck in the design of hardware and RTOS. That's why we think our framework can work well. And this picture shows the benefit and the special point of the fine-grained lock design. We can see in the normal part, we can see in the right picture, in the normal part, the fine-grained lock works very well, And when the storage reaches the maximum, we can see the performance may be worse than the giant log design. So how to control the balance between the giant log design and the fine grained log design should also be a very interesting topic. And we can find such interesting topic just using our benchmark framework. And this is another interesting point of our benchmark frameworks. And so as the scalability evaluation, we can also see the overall performance behavior of the multi-core systems. And also we can see some interesting features of the hardware and RTOS. For example, on the right hand, the picture shows that when the active core is increasing, the behavior of the NATEX RTOS is very strange. Some cores do not work when 6 cores are activated. This is just because maybe the memory is limited. And such figure shows the problem in the design of the RTOS or the devices. And then I will give you the conclusion and the future work of my work. And we designed a flexible benchmark framework for embedded systems and optimized and implemented our former multi-core benchmark methodology and built and evaluated the prototype on 3 different systems and obtained the performance characteristics and some feature and bottleneck of our systems. In the future work, we want to expand our method to more representative RTOS and hardware platforms and integrate modules such as performance monitor unit in ARM to enable deeper analysis of our performance data. And we also want to optimize our benchmark scenarios by concerning real-world task feature, which is my next topic. And that's all of my speak. And thank you very much for your attention.
Thank you very much. Any questions for Xiaoying? Any questions or comments? So yeah, I have one, which is pretty much high level. So you mentioned in the paper you have 3 system prototypes to evaluate your benchmarking frameworks.
Oh, yes.
So why you chose these 3 systems? Any particular reasons?
Yes. One reason is we want as many core as possible. So we chose some multi-core devices. For example, Sony's Presence have 6 cores and the X-Core AI have 16 cores. And the other reason is we want to test as much type of RTOS as possible. For example, NATEX is a POSIX style RTOS, and on the other hand, the Topaz FMP is Japan-made RTOS with fine-grained log design, which are seldom seen in the state-of-art RTOS. So by testing them, we can see some difference between the devices and the RTOS systems. And from this, we can see some idea when we further design or develop the RTOS or devices.
Okay. Yeah, thanks. I think in the interest of time, so we move to the next speaker. Thank you. Okay, so we have Yan Shen to present his paper, Efficient System Call Interception for ARM. Yeah, feel free to start.
Thank you. Thank you for your introduction. And good morning, everyone. I'm Yang Shen from National University of Defense Technology. Today, I will present ASE hook, an efficient system call interception for ARM. Here is the outline of today's talk. First, I will cover the background, then introduce our ASE hook design, present the experimental result, and finally discussing the elimination and the conclusion. Let's begin with the background. Intercept thesis code has various applications such as program chasing and debugging, improved reliability and security, emulating different operating systems, but still face inefficiency in ARM. Recently, Yatsuda et al. Proposed a new method for x86 called the poll line. As illustrated in this figure, the RAS register holds the physical number. The poll line replaces physical instruction with a 2-byte CoQ star RAS register instruction along the program to jump to the virtual address between 0 and the maximum physical number. A trampoline is placed at the address 0, so when execution reaches that entrance, it jumps into the trampoline routine. This design guarantees efficient syscall with a minimized overhead in x86. However, this approach faces challenge on ARM platform. The first challenge is that the ARM architecture requires instruction to be 4-bit aligned. If a similar instruction to CoQ star RAS directly used on x86 is directly used, it may jump to a long-aligned address and resulting in a bus error. The second challenge concerns returning to the original control flow after the jump. ARM don't have an instruction like CoQ and can jump and push the return address onto the stack. Using a BL instruction, batch and link, would overwriting the important S30 register, which store the return address of the last function call and is clearly unacceptable. Now, so therefore, our work focus on overcome this challenge to enable efficient system call interception on ARM. Now let's move into the method section. To solve this challenge, we have two key observations. First, the total number of SVC instructions with a processing memory image is very limited, especially for high-level language users who typically rely on the second system call for shared library rather than writing SVC instruction directly. Table 1 shows that the number of SVC instructions in the process image of the sum of the applications, with most have fewer than 1,000. Second, for most system calls, at least 2 instructions can be replaced. Based on the ARM architecture, the system call number must be passed to the S8 register before exiting the SVC instructions. Therefore, we can at least replace the SVC instruction and the instruction that assign the view to the S8 register. Table 2 shows for each application how many SVCs are actually used and how many of them cannot be intercepted by our 2 instruction replace method. Only Negas and Apache has such remain SVCs, which further validate our observations. For that one remain SVC in Negas and Apache, we fall back to signal-based interception. The signal-based interception works by using BRK or illegal instruction to replace SVC, which allows a signal trip or signal yields, respectively, allowing us to catch the system call while signal handlers. However, it requires a frequent user model to kernel mode transactions and thus incurs significant overhead. We therefore use this approach only as a fallback method. Based on the observation above, we devised our replacement strategy and the trampoline design. This figure gives an overview of ASC hooks. Our approach targets each SVC instruction and its preceding move S8 physical number of operation for replacement. Our replacement strategy includes 2 methods. First, we use the move instruction to load the address of the first level trampoline near the destination register S8 and replace SVC instruction with the BR instructions. This method is limited by the constraint of the move instructions, which accept only a 16-bit immediate view. Consequently, the reachable virtual address range is limited to the range from 0 to the 65,535, or coordinating a total number of 3,383 instructions. According to our trampoline design, each first level trampoline requires 4 instructions, allowing for up to 3,840 trampolines. However, as previously observed, the number of SVC instructions in typical application is very limited, making it almost impossible to reach this limit. This method currently serves as our primary replacement approach. Second, we use ADRP instruction to load the target address into the destination register S8 Again, replace SVC instruction with the BR instruction. Since the ADRP produces a page-aligned address, tropically multiplays at the beginning of the memory pages lead to significant overhead. Therefore, we use this method only when the first method reaches the limit. Although we have not yet encountered application that requires this fallback, it retains as a precautions. This design guarantees a 4-bit aligned jump and avoid the issue of misaligned jump address. Our trumpeting mechanism addresses 2 key challenges. The first challenge is restoring the original instruction flow after incepting a syscall. Using BLR to jump with overwriting the S30 register, directly push the return address onto the stack with requiring replacing additional instruction, which is not feasible. Our solution is to design a dedicated trumpeting for each SVC that push the address of the instruction following the SVC onto the stack. Then this allows us to retrieve the return address from the stack after inserting the SVC in the trumpeting. The second challenge is limited immediate view range of the move instruction, which is restricted to CT bits. This limits the directly jumpable virtual address range from 0 to the 65,535. Make effectual use this narrow range critical. To overcome this, we design a multi-level trumpeting scheme. We implement a 3-level trumpeting hierarchy. The first and the second level are dedicated to each SVCs, while the third level is shared across all system calls. Level 1, a 4-instruction sequence that quickly redirect execution will minimize address space usage. Level 2, trumpeting first re-executed the previously replaced assignment instruction to restore the original views of the S8. Then it pushed the return address, as the instruction following the SVC, onto the stack and transfer control to the third level trumpeting. Level 3, upon entering the trumpeting, the register content is first saved. Next, the user provided hook function is called. After that, the register state is restored, the original control system call is executed. The return address is popped from the stack to resume execution at the original instruction flows. This multi-stage trumpeting design effectively solved both return address preservation and limited jump range challenge. However, if jump target fall between the two replaced instructions, the first instruction, which assigned the first level trumpeting to address to S8, may be skipped. This results in an incorrect jump target. To handle such edge cases, we fall back to replace such SVC instruction with a BRK or illegal instruction to intercept through Synchronous. We propose 3 methods to identify such cases. First, if no assignment to S8 register is found preceding the SVC instruction, we intercept this SVC using Synchronous. Second, for directly jump instruction, we inspect all directly jump instructions in the process memories and calculate the target address. If the jump address falls between the 2 instructions, we switch to signal-based handling for corresponding SVCs. Third, for directly jumps, if the jump target falls between the 2 replaced instructions, only the BR-S8 is executed. Since the S8 contains the signal number, this inevitably triggers a segment fault or bus error. With the signal handler, we perform further analysis. The PC views equals the S8, which is equal the signal number, and the S8 certainly contains the return address. Using this information, we can infer the signal number and also recover the address of the original SVC instruction. We are appending this data to a configuration file for further use. These methods are rarely triggered in practice. The main purpose of this method is just for insurance. Now let's dive into experiments. Our experiment was performed on ARM platform. The configuration is shown in the slide. We compare ASC hook with ptrace, signal interception method, and LD plot. First, we measure the overhead of intercepting a single signal system call using gate PID as the test cases. To eliminate the kernel cross system call overhead, we use a hook function that returns virtual views. Shown in table 3, LD plot has lowest overhead. AIC hook incurs about 5 times of LD plot, while signal interception and ptrace are 29 times and 61 times of the AIC hook respectively. sorry. To evaluate the overall runtime impact of AIC hook, we select SQLite, use its speed test 1 benchmark, and MPI BFS. MPI BFS is our own implementation of the branch first search algorithm using MPI and be open sourced together with the rest of the project code. As the figure 3 shows, AIC hook is just 0.3 seconds of the overhead, only 3.3% of the SQLite speed test 1 runtime, total runtime. While for BFS, its overhead is merely 0.3% of the overall execution times. We select Redis, Apache, interval or random, Iowa, and Negas as a benchmark program to elevate the impact of AIC hook on application throughput to minimize the impact of inter-host communication. We select both client and server on the same machine. For Redis, we use its built-in benchmark tools. For Apache and Negas, we employ WRK to generate HTTP workloads. As shown in figure 5, the throughput degradation caused by AIC hook is significantly lower than other two methods within the performance drop of 0.96%, 1.77%, 4.98%, 9.94%, and 4.8% for application listed in order. To investigate the impact of the signal transfer size on performance degradation in fail IOs and the network throughput, we conduct further tests on read bandwidth of IOR and Negas throughput. For IOR, we adjust the single transfer size. For Negas, we change the size of the return static resource fields. The results show that for IOR, a single transfer size increased, bandwidth steadily improved, approaching the device bandwidth limit, while the performance degradation caused by signal interception tools gradually decreased. For example, AIC hooks overhead dropped from 9.94% at 1 kilobyte to 1.97% at 64 kilobytes, mainly because the proportion of the system call overhead with the entire I/O stack decreased as the transfer size increased. For Negas, a similar pattern is observed. AIC hooks performance degradation dropped from 4.8% at 0 kilobyte to 1.4% of 1 megabyte, while p-trace drops from 35.3% to 21.8%. Furthermore, compared to other two methods, AIC hook consequently exhibit low overhead across all fail size. The next up is part for conclusions and limits. Limitations of the AIC hooks. Due to our first replacement strategies requiring for low virtual address, AIC hook is not supported on Windows or Mac OS. On the both platforms, virtual address location is either restricted or fails by default. However, we can completely avoid using the first replacement strategy, and instead on the second replace strategy, it may solve this issue by resulting in a significant memory overhead. AIC hooks use LD preload to replace SVC instruction before application startup. Any SVCs in the library load later, for example, while still open, will not be hooked. We can address this issue by adapting the online binary rewrite approach proposed in S containers. Since our tools register signal handler before application startup, they may be overwritten by the application's own handlers. However, even without using signal for interception, our first two method strategy can meet the need of the most applications. Moreover, most applications at least do not intercept signal generated by debugging information instructions. The virtual dynamic share object enables user space program to access certain syscalls directly by expose their implementation through the kernel. AIC hooks don't support hooking VDSO-based system calls. However, we can disable VDSO to address this issue. In edge cases, AIC hook may encounter some performance bottlenecks. For example, if the total number of SVC for a process is exceeding the 3,840, or if the BRK or illegal instructions are repeatedly executed, the overhead could become significant. However, as shown in the table 2 and the evaluations, there are extreme cases and rarely occur in practice. In conclusion, we present AIC hook a system call hooking mechanism for ARM. It ensures efficient and comprehensive interception through a novel urban design. We intensively test AIC hook with real-world application, demonstrate its comprehensive and efficient interception capability. The experiment results indicate that AIC hook maintains an average performance overhead of 3.8% for most system call intensive application. Our implementation is open source and available at the link shown on the slide. Let's conclude my talk. Thanks for your listening.
Thank you. Any questions?
So you have shown an overhead with the LD preload variant, at least on one of your benchmarks, right?
Yes, because
Could you explain what you do exactly? Because I don't think LD preload allows you to change the instruction, just to override functions.
pardon?
So when you use LD preload as one of your comparison base, right?
Yes.
What exactly do you do to intercept the system call at that level?
Oh, please wait a minute. LD plot is I chose LD plot because it is a symbol of the function method to intercept the system calls, and the character of this method is very fast, but it very hard to hook all of the system calls, and so it's very difficult to employ it. It takes a lot of work to employ it to all of the application we test, and we think that although it is efficient, but it can't cover all the system calls, because the system calls may appear out of the function, or in a function it will appear multiple SVCs, and whether it can do intercept all of the system calls with its function in practice, I really wonder it is possible in the practice.
Okay, thank you.
Okay, thank you. Any questions? More questions? No? Okay. So I have a quick one. So what are the key challenges compared with the x86 paper, the Z-Polan, in 2023?
2023?
Yes. So assume that there's a bunch of binary translation tools available, and the x86 they have done this interception with very high performance. So what are the key challenges for doing this on ARM?
First, the ARM architecture, although we first introduced the Polan, and here's a very beautiful work, interception, the system calls in the x86. But he has, according to his method, he will has two challenges. First, if we use the CoQ star AS to jump to the virtual address, because ARM's instructions must be to address to 4-bit aligned. If we directly jump to the use his method, the physical numbers will not always multiply of the 4, so it will cause a bus error. And the second challenge is restoring the return the original control flow after the exception. The x86 can push the address. The CoQ instruction can push the address of the system calls, and but in ARM it don't have such a function calls instructions. The BL instruction will overwrite S30 register, which store the last function calls return address, and it will ruin it. So it is not feasible.
Okay, thanks. I think join me to thank Yang again, and let us move to the next speaker. So our next speaker is Zhongwen Yang. He's paper title is Energy Efficient Selective Scheduling for Fast Frontier Transformer in Embedded GPUs.
Okay. Hello everyone. I'm Doan Yang from Korea University, and I appreciate the opportunity to present our research at STS. Today I'll be presenting SSFFT, our approach to energy efficient selective scaling for fast Fourier transform in embedded GPUs. Let me begin with a brief introduction to the fast Fourier transform, or FFT. FFT is a fundamental algorithm used in many domains: signal processing, image analysis, communication, and machine learning. It computes the discrete Fourier transform efficiently, which is critical for converting data between time and frequency domains. Embedded GPUs in edge devices are increasingly used to accelerate FFT workloads. They provide parallel processing power that is essential for real-time performance in applications like LiDAR, IoT sensors, and even edge AI inference. However, embedded GPUs operate under strict power constraints. This makes energy-efficient FFT computation a critical challenge. Despite their potential, embedded GPUs face several limitations. First, static thread block allocation has limitations under varying workloads. As a result, streaming multiprocessors or SMs in GPU are often idle or poorly utilized. Second, there is no cache-friendly kernel design, leading to poor L2 utilization. Here's today's outline. First, I'll go into more detail about challenges in FFTs. Then I'll introduce our proposed solution, SSFFT. We'll look at its design principle, the algorithm, and how it handles memory more efficiently. And finally, we'll evaluate the performance and energy efficiency of SSFFT. CUFFT is NVIDIA's optimized FFT library, widely used in many GPU-based applications. CUFFT statically determines grid and thread block dimensions based on only FFT length and patch size. This might sound reasonable, but in practice it causes problems. For instance, if the FFT length and patch size are small, the number of generated thread blocks is also small. This means only a few SMs are actually active during execution. As you can see in the diagram, small FFTs result in sparse utilization across the GPU. This leads underutilization of available compute units and low throughput per watt. This graph shows the throughput per watt based on the number of active SMs. As we increase the number of active SMs, the throughput per watt improves significantly in FFT workloads. In particular, it achieves 2.5 times better throughput per watt if the number of active SM is maximum. There's another inefficiency of static allocation. In CUFFT, each thread block for the same FFT length always uses the same shared memory size and the same thread block size. As shown in this diagram, thread block 1 and thread block 2 are allocated equal portions of shared memory and compute resources. If the batch size is small, only a few thread blocks are allocated in SM, and the large portion of shared memory go underutilized. Also, imbalance between the size of shared memory and thread blocks result in underutilization of shared memory. Because of constraints in computing unit allocation, once the available computing resources are fully assigned, additional shared memory resources cannot be utilized. The size of utilized shared memory determines how many FFTs can be computed in parallel in an SM. Low utilization of shared memory reduces concurrency and throughput of GPU. And for larger FFT sizes, CUFFT splits the FFT computation into two kernel launches because it can't fit all intermediate data in shared memory. This results in frequent memory transfer between global memory and L2 cache. To illustrate how data movement of large length FFT works in CUFFT, we walk through an example. In this scenario, we perform 4 FFTs, but the L2 cache can store data for only 2 FFTs at once. In the first kernel execution, the GPU begins by processing FFT1. As part of this process, the data for FFT1 is not only computed, but also stored in the L2 cache. Then FFT2 is processed in a similar manner, and its data is also placed into the L2 cache. At this point, the L2 cache holds data for both FFT1 and FFT2. Since the cache can only store 2 FFT's data, there is no remaining space for any additional FFT data. When the GPU proceeds to process FFT3, it needs to load FFT3's data into the L2 cache. However, since the cache is already full, the data for FFT1, which was stored earlier, is evicted from L2 cache to make room for FFT3. The same issue repeats when FFT4 is processed. To store FFT4's data in the L2 cache, eviction of FFT2 must occur. Now the cache contains data for FFT3 and FFT4, not for FFT1 and FFT2. In the second FFT kernel, the GPU needs to access the data for FFT1 again, since the computation is performed in 2 stages. However, FFT1's data has already been evicted from the L2 cache during the processing of FFT3. As a result, when the second kernel attempts to load FFT1's data, it encounters a cache miss. This triggers an option memory access. Such accesses are significantly more costly in terms of both latency and energy. This overhead is not just limited to FFT1, the same issue can occur for FFT2 or any other FFT whose data was previously evicted. Ultimately, this results in inefficient memory uses and degrades both performance and energy efficiency. Now that we've identified the limitation of CUFFT, let's take a look at how we address them. We propose SSFFT, selective scaling for fast Fourier transform. The key idea is to dynamically scale how thread blocks and threads are allocated for each FFT based on workload characteristics. This allows us to keep SMs and shared memory highly utilized even under varying workloads. Additionally, our kernel is designed to better utilize the L2 cache, reducing memory interference between FFT stages. Let's first take a look at how the selective scaling algorithm works. In the case of small length FFT, the original CUFFT assigns only one thread block per FFT. While this approach is straightforward, it often results in poor SM utilization, especially if the batch size is small. In contrast, SSFFT computes the appropriate number of thread blocks to better utilize SM resources. It then determines how many thread blocks to allocate per FFT based on the batch size. This dynamic assignment helps ensure that available GPU resources are used more efficiently, even under varying workload conditions. Moreover, we carefully choose thread block size to better utilize shared memory. This design enables each SM to better benefit from parallel execution. As a result, SSFFT achieves high energy efficiency regardless of FFT length or batch size. To further improve in efficiency, we merge two FFT stages into a single kernel. We divide the input into partitions that fit within L2 cache. By keeping intermediate results in cache, we avoid option memory access. The partition size, denoted as A, is carefully chosen so that FFT stages fit in cache. We set the partition size A to be no more than 25% of the L2 cache so that the working data can fully reside in cache and maintain a high cache hit ratio during execution. Once the partition size A is determined, the input is split into K partitions accordingly. As a result, completing all FFT operations requires K iterations in total. This diagram illustrates how data movement is handled in SSFFT. Similar to CUFFT, the data for FFT1 is processed first and stored in the L2 cache. Then FFT2 is processed and its data is also placed into the cache. However, unlike CUFFT, SSFFT proceeds to perform the second FFT operation using the data from FFT1, not FFT3. Since FFT1's data is still in the L2 cache, this results in a cache hit. This reuse of data within the cache significantly reduces option memory access and improves overall efficiency. In the same way, the second FFT operation is performed for FFT2. Its data is still available in the L2 cache. This also results in a cache hit, allowing the operation to be proceeded without any option memory access. In the same manner, the first stage FFT operations for the next partition, FFT3 and FFT4, are carried out sequentially. By keeping the necessary data in cache across both FFT stages, SSFFT minimizes option memory access and improves both performance and energy efficiency. Next, we evaluate the performance and energy efficiency of an SSFFT. We tested across FFT length for 1K and 256K and batch size from 1 to 128. We measure two key metrics, performance and throughput per watt. The baseline is CUFFT. We evaluate SSFFT on the NVIDIA Jetson Orin AGX. This graph shows speed up based on the batch size for the 1K length FFT. For the 1K length FFT, SSFFT achieves a 1.35 times speed up over CUFFT. This improvement is more significant if the batch size is small. It is because SSFFT increases GPU utilization by allocating thread blocks more efficiently in low batch scenarios. And this graph shows the normalized throughput per watt based on the batch size. In terms of energy efficiency, SSFFT achieves 1.29 times higher throughput per watt. This alone shows that SSFFT can effectively overcome the underutilization problem that arises if the batch size is small. In the 256K length case, SSFFT achieves a 1.27 times average speed up across all batch sizes. This contrasts with the 1K case, where the speed up is barely observed if the batch size is small. Here, the improvement comes from higher L2 cache efficiency, which reduces memory latency during data loading. It is independent of GPU resource utilization. Following the same pattern, SSFFT achieves 1.25 times higher throughput per watt consistently across the batch size range. SSFFT enables data reuse without unnecessary cache eviction. As a result, it offers better performance and energy efficiency compared to conventional approaches. Finally, we summarize the impact of SSFFT. Enhancing energy efficiency is critical for embedded GPUs. CUFFT struggles with underutilization and memory inefficiency. Our proposed SSFFT dynamically allocates thread blocks and merge kernels to address these problems. SSFFT achieves significant improvements in both performance and energy efficiency. We believe SSFFT is simple, practical, and scalable solution for real-world embedded systems. Thank you for your attention.
Thank you very much. So, any questions for him? Comments? Yes.
Thank you for nice talk. I have a simple question. So, have you thought about thermal issue? My question means that if we increase the GPU utilization, it leads to increasing GPU temperature. So, have you thought about this issue?
In fact, we don't consider the thermal issue importantly, but we tested from the real GPU model using the Jetson, NVIDIA Jetson. So, the result can be viewed as the thermal issue considered result.
Was the answer your question? Yes. Okay. So yeah, maybe one more question before we move to the next speaker. Any?
Can you go to the evaluation section? Whatever will be fine. Oh, okay. My question here is what is the performance trend of the CUFFT when increasing the batch size? So it is normalized to the CUFFT. So I'm curious how the performance trend when increasing the batch size.
Pardon, can you tell me one more time, please?
My question is that your performance gain over the CUFFT with the small batch size, it might be because the CUFFT performance might be really low. So I'm just curious for the absolute performance of the CUFFT.
Absolute performance of CUFFT?
Absolute performance trend, performance change over the different batch size of the CUFFT.
The CUFFT shows the lower energy efficiency in lower batch size, and the energy efficiency of CUFFT increases as the batch size increases.
So if the batch size increases, would you still outperform CUFFT significantly?
In the small FFT length, the batch size is sufficiently large than the CUFFT, and SSFFT has the same performance and energy efficiency.
Okay. Yeah. Did that answer your question? Okay, cool. Join me to thank Dongwen again. Thank you. Let's move to the next speaker. So our final speaker in this session is Marcus. His paper titled An Ownership-Based Virtually Non-Valid Heap for Embedded Systems. So once ready, feel free to start.
Okay, thanks for the kind introduction. As already said, I'm Markus Elias Gerber, and today I'm really happy to present to you our work called V&V heap, a ownership-based virtually non-volatile heap for embedded systems. But now first let's look into why our work is relevant. So there exists a set of devices called intermittent systems. These systems are self-sustained and do not rely on any external power connection to an external power grid, for example. Instead, they harvest energy through, from their environment through using, for example, energy from light or radio waves. Additionally, they do not use any batteries, but make use of small and environmentally friendly capacitors. Overall, this makes the system really small, portable, and cheap to produce. However, this device architecture comes with great challenges. So to get a better understanding at these challenges, now let's imagine a specific intermittent system and look at the following plot. So on the left-hand side, you can see the system's input power, and on the right-hand side, we can see the system energy. Let's imagine the system starts with a high amount of system energy. After some time, the input power decreases and the system energy reaches an operation threshold. At this point in time, the system is powered down, and this is basically called hard intermittency. So we power down our device once we reach that operation threshold. After some time, the input power increases again, and we reach that operation threshold again, and so we power on our device again. However, there's a major challenge here because most of the devices actually store most of their state on volatile random access memory. So once you power down your device, you lose all of your state. However, the problem is that most of the devices want to actually resume their state, so we need some kind of state retention mechanism to persist our state once before we power down and once we reach our operation threshold, and restore our state once we reach our operation threshold again and once we power up our device again. However, this is pretty challenging as you only have limited energy to do so, and you need to persist your state in time. This is especially challenging for devices with large amounts of state. And nowadays, there exists many applications on low-power devices that you want to run on these devices. For example, memory-intense applications, for example, deep neural networks or large language models. And also specifically to intermittent systems, you might want to store certain work packages if you have a low amount of energy available and defer them to a point in time where you have a high amount of energy available again. And commonly, these types of state or data is explicitly allocated, for example, in heaps. So now let's look at how do we even persist our state? So how do you persist state before the system shuts down? You basically copy data from volatile random access memory to non-volatile memory. What data should you persist once you're about to reach that operation threshold? Should you persist all of the volatile state? And this is actually a bad idea. As I said before, your state can be really large, and you only have a small portion of energy to persist your state. So what you can do alternatively, you can persist your state at the start, and then once you reach the operation threshold, only persist the amount of modified state. And as we only have a limited amount of energy available, we also can limit that amount of modified state at any time, so we can be sure that we persist our state correctly. The main takeaway here is that we need precise modification tracking to do that. So let me introduce you to a few approaches how to do that. So a naive approach would be to leverage MMUs. So MMUs are commonly used on desktop systems to translate virtual addresses into physical ones. And they are safe to use, they provide transparent swapping. However, they are not predictable at all, so many applications, for example, databases, use complex mechanisms, for example, logging, undoing, and redoing operations to overcome this issue. They're also not hardware agnostic, as you need special hardware for that. So, and I really want to stress that the devices we target here, these intermittent systems, are low-power devices, so for example, microprocessors, and they typically don't have an MMU at all. So this is not feasible at all. There exists a second set of approaches, and these are software-only approaches. And managed state as a related work is one of them. So you basically employ managed state alongside your main program, and then every time you're about to modify data, you notify managed state that you start modifying data, and then you notify managed state when you are finished modifying data. However, the major issue here is that this API isn't enforced at all, and you can easily forget it. So basically in line 6, you might risk the integrity of your entire application. So let's summarize managed state. So it is hardware agnostic. It is implemented and employable as a software library. It is also predictable. However, it doesn't provide any transparent swapping. So if you have large applications where your memory requirements exceed your physical memory, you cannot have any swapping, and you need manual programming effort to provide like swapping-like behavior. It is also not safe to use, as we saw before. And now let me introduce to you our virtually non-volatile heap, which basically solves all these issues. But how do we actually achieve this? So our main idea here is to leverage modern programming languages by using the concepts of ownership and borrowing. So these two concepts are generic to programming languages and are implemented in multiple different ones. However, for this talk, I'm focusing on Rust here because it's the most famous example of a programming language implementing these two concepts. So basically, ownership tells you that each value has an owner. There exists only one owner at a time, and the value is dropped once the owner goes out of scope. The definition for borrowing is basically that there exists either exactly one mutable reference or any number of immutable references. And the advantage of these two concepts are that they are zero-cost abstractions as they are statically checked. So now let's go back to our previous example of an unsafe way to do a software-based implementation. So we now can use these two concepts and implement or design our virtually non-volatile heap to treat memory as a resource and guarding that resource with borrowing and ownership. And with that, we can transfer this example and make it completely safe. And if now this API is enforced, and if we forget to use that API and modify memory, the program is rejected via a compilation error. And overall, this makes software-based modification tracking and swapping safe. So now let's look at a practical example. So let's imagine we have a specific intermittent system that stored multiple IP packets to be processed later, and now, currently, we have a high amount of energy available, and now we want to actually send these IP packets. So now let's first send the first IP packet. We dequeue it from a list, and now we want to retrieve a mutable reference to our virtually non-volatile heaps API. You can see basically that all of these packets are currently swapped out. They are exclusively located in non-volatile memory. And once the user requests a mutable reference, the virtually non-volatile heap will make that packet 1 resident, mark it as modified, and pin it into memory so it doesn't get unloaded. After that, the user can transparently modify that object by, for example, calculating a cyclic redundancy check. After that, the user can drop the reference again, which makes the packet not pinned anymore, and then can send that packet. Now let's send the second packet. We dequeue it from our list again, retrieve a mutable reference, and yeah, the virtually non-volatile heap will make that packet 2 resident again. And now let's say our intermittent system has a constraint that it only has energy to persist up to 1 IP packet once the operation threshold is reached. And this constraint can be enforced by the virtually non-volatile heap. So in order to make packet 2 modified, we have to first persist packet 1. So the virtually non-volatile heap persists packet 1 and then marks packet 2 as modified. Then also pins it into memory. And then the user again can transparently modify that memory. Then the reference can be dropped again and the packet can be sent. Now let's send our third packet. We can dequeue it from our list again, retrieve a mutable reference, and now you basically see, okay, we don't have any more memory in our random access, or no more space in our random access memory left. So the virtually non-volatile heap will have to first unload a packet. So in this case, it chooses packet 1, unloads that packet, and now it can make packet 3 resident. And we still have our constraint, so before marking packet 3 as modified, we have to, persist packet 2. And then we can mark packet 3 as modified, pin it into memory, and then the user again can modify that object. So let's come to our evaluation. So we evaluated our virtually non-volatile heap on an ESP32C3 microcontroller and use a FRAM module as non-volatile memory. Basically, for the first evaluation, we compared our virtually non-volatile heap with a module-based approach. So basically, this module-based approach is an approach where developers notice that they have 2 less physical memory available, and so they split their applications in different modules, and only one module is swapped in at a time. So you can think of it, or it's conceptually similar to early computing systems where you only had one process running at a time, and only one process is swapped in at a time. And yeah, we then measure the latency of accessing objects in a best, a bad, and a worst case. And in the bad and worst case, the scaling is different than in the best case. So in the bad and worst case, the numbers are 100 times larger. So the takeaway here is that our more fine-grained management of objects reduces the swapping overhead up to 93% in the worst and relevant cases. So we then compared our virtually non-volatile heap to the managed state, the related work. We implement an embedded key value store that uses 32-bit integers as the keys and a wide variety of different values. We then measure the average latency for reading and modifying these values sequentially and in a sequential, unequal, and random pattern. Contrary to the virtually non-volatile heap, who does object-wise modification tracking, managed state splits memory basically into different chunks and then performs modification tracking on these chunks. And these chunks are called pages in their case. And because they do this, because their system has no notion of objects at all. They just see raw memory. And yeah, we just do our experiment with different page sizes. And we can see that our virtually non-volatile heap provides similar and/or balanced performance while providing more features, and these are non-volatile memory safety and transparent swapping. So to come to my conclusion, we introduced the virtually non-volatile heap, which provides non-volatile memory safety, so it guarantees that programmers can't make any mistakes. It also provides transparent swapping capabilities, so there's no manual effort required to use swapping even on low power devices that do not have any MMU. And we achieve this by treating memory as a resource and guarding that resource with ownership and borrowing. It is also predictable as it provides worst case guarantees and improves these worst cases with object-wise modification tracking. Finally, it's hardware agnostic as it's implemented and employable as a software library. And finally, here you can see a link to our paper and our link to the publicly accessible implementation and evaluation artifact. So thank you for your attention. I'm looking forward to answering your questions.
Any questions? Thank you for a nice talk. Can you go one slide back?
Yes.
Yeah. So how is it predictable? What is predictable in your mechanism?
So it's like focusing that once we reach our operation threshold, that we can guarantee that, yeah, we persist our state in time. So we limit our state that is modified at a time, and if we do so, we can limit the amount of energy that is needed to persist our state. So that means predictability.
Okay, yeah, thanks. So I'm wondering from a compiler perspective about these annotations that you have to put in. Of course, one might think, well, how difficult it is to put these annotations automatically. So what's your take on that?
Yeah, that's, we also talked about this in the paper. So basically, Rust provides features where you can have like macros defined at a function, for example, and then you can basically insert these function calls, like get a mutable reference. So basically, you would use an object as you would normally, or you would think you would use an object as you would normally, but if you use that macro, we can insert these calls. So if you access an object, you can insert that call to access a reference, for example.
And if I may ask, so what would be the price to pay for using these macros? Would it provide then, would it cause more overhead than if you smartly did it yourself manually? Is that the point?
Yeah, I guess so. I mean, for example, if you access the same object twice after another, I guess with a macro-based approach, like a naive or a simple implementation would be every time you access the object, you would retrieve a reference, and after you access the object, you would drop it again. And for your second access, you would then again retrieve a reference and then drop that reference again. But I think the overhead isn't that high because the main overhead is like swapping in objects and persisting objects, and it's only like a really small overhead compared to these swapping in and swapping out. These are really the costly operations.
Thank you. So any more questions? We have a few more.
I have a simplification. So the proposed methods give a predictable checking pointer depending on a worst case energy consumption. But the available energy can change a lot depending on environmental factor, like how much energy is being harvested. So have you thought about how to handle this energy fluctuation at runtime?
I'm not sure if I 100% understood your question correctly. Like, do you mean that the amount of energy that you can store in a capacitor can change according to like temperature, for example, or yes?
Yes, yeah, right. Yeah.
Okay. No, we didn't look into it at all, but I think, like, is your question that maybe it's possible to like dynamically at runtime change the amount of modified state, so that would be possible as well. So, but we didn't look into it at all, no.
Okay, yeah, thank you.
Okay, thank you.
Thanks for the great talk. So one problem of using like very strict borrower and ownership model is that there are certain programs that are banned unless you resort to using reference counting or unsafe features. For intermediate computing case, have you seen any of those cases, or is it not that useful here?
So your question is if you can use unsafe code,
or like more partially, do you have situations where your ownership-based approach was too strict, so you had to go to RC route or unsafe route?
Currently not, no, but it is possible to, like, you retrieve a mutable reference or you retrieve a reference through our API, and you of course can use it as a pointer and then unsafely access that pointer. But yeah, the virtually non-volatile heap provides guarantees that like the object is swapped in until you drop that reference again. So you can use unsafe code safely until the object is swapped out or could be swapped out again. So yeah, that could be possible.
Any more questions? Okay, if no, we draw the close of this session. Thank you again. And we have lunch. I think yesterday lunch is Orchid. I guess we have to move to the biggest room. So you get out of this room and turn left. This is the largest room there. So we all sit in the room, have lunch. Yesterday was a lunch box. I don't know. We expect a
Uh, 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 uh,
thanks. Okay, let's get started. Welcome to the first session in the afternoon. My name is Yuno. I'm working at the Korea University. I'm very honored to run this session. So we have the 4 fantastic talks in this session, and let's get started. The first talk is JetCert. It's from the Arman at Shahid Beheshti University. We are going to watch the pre-recorded talk, and we are going to try to have the online Q&A session if possible. But due to the urgent situation in Iran, a domestic situation in Iran, we may successfully do the Q&A or not. So it depends. So let's try. First, let's watch the pre-recorded talk.
Hello everyone, my name is Arman Shamidari and I'm a graduate with a Bachelor of Science in Computer Engineering from Shahid Beheshti University. Today I want to present a paper I co-authored with my professor, Dr. Mehran Ali Dusnia. I'm sincerely grateful for his guidance and support. In this paper we introduce a framework called JetCert. JetCert is a self-adaptive compilation framework for fast and safe code execution, which is also the title of our paper. Let me begin by introducing the capabilities of the JetCert framework. JetCert designed for embedded and safety critical system, and it focused on establishing an optimal trade-off between safety guarantees and system performance in embedded and safety critical systems. JetCert has a MAPE control loop that can monitor system states at defined intervals to maintain system objectives, and MAPE stands for monitor, analyze, plan, execute, and knowledge. Besides, JetCert has a priority-based CI/CD pipeline for dynamic change management in embedded and safety critical systems. My motivation for designing this framework is first absence of a critical strategy for modern embedded and safety critical systems, second, development of a practical framework to address a fundamental software challenge, and finally my long-standing passion for the intersection of software and security. I'm very interested in these 2 areas. So the main problem is that we have an embedded or safety critical system with a set of requirements called R. Each requirement has M versions denoted by V, and each version is just either safe or fast. We want to select the best version from V for every requirement in each period of the MAPE loop, in which the total utility of the safety critical system is maximized. Before looking at the architecture of JetCert, let's review the necessary background. First, the concept of self-adaptive systems. Self-adaptive systems are computing systems with built-in capabilities to automatically adjust their behavior when their operating environment changes. These systems track their state and environment, detect significant change, and respond autonomously to meet objectives. The core defining characteristics of self-adaptive systems exist in their closed feedback loop known as the MAPE control loop. The adaptation process follows explicit adaptation goals and policies and constraints. For the second, certified compilation represents a strict compiler method requiring formal proofs to ensure compiled code preserves program semantics and generates mathematical certificates that prove compiled code behaves identically to source code. The method proves essential for safety critical system by ensuring the highest possible confidence level, and for example, ComCert is a certified compiler that we used in JetCert. And J8 compilation combines interpolation and static compilation features. Through dual execution, the code first gets interpreted, then detects hotspots to enable dynamic compilation and stores it for future use. The system performs optimization based on runtime profiling data collected during execution to guide optimization decisions. And for example, Namba is a J8 compiler that we used in JetCert. So it's time to examine the architecture of JetCert. Developers of safety critical systems, to design and implement their systems within the JetCert framework, must first divide the system requirements into two distinct categories. The first includes requirements that need the establishment of an optimal trade-off between safety, system safety and performance. We designate these requirements as the self-adaptive requirements because they need to adaptively shift between two different compilation paths. The second includes requirements that utilize a fixed compiler path. We refer to these requirements as the other requirements. JetCert manages and adaptively executes self-adaptive requirements according to changing specification in the environments, while other requirements proceed through their native runtime paths independent of JetCert control loop. To use JetCert, developers should implement self-adaptive requirements in modules structure and provide them as input to the JetCert framework. Modules is a structure in which developers of the embedded application implement each self-adaptive requirement in the form of a module structure. Additionally, developers of safety critical systems define the shift conditions between different versions of each module using the MAPK rules structure, which will be discussed later. And module is a structure in which developers of the embedded application can implement several versions to satisfy self-adaptive requirements. At runtime, JetCert adaptively shifts between different versions of each module based on the captured change in the environment. The core is the central part of JetCert that is responsible for managing and maintaining the modules structure. The core consists of two components named modules management and versions management. The modules management stores the state of each module and runs version of each module in the current period. The modules management part provides adaptive runtime capability to developers, allowing them to respond to user requirements based on the current situation. Adaptive runtime is an interface that adaptively responds to requests. The versions management records the state of each version and determines how each version should be compiled and executed based on its configuration file. If needed, other JetCert components can request version management to compile or execute a version. JetCert, by implementing the MAPK loop subsystem, monitors the system and the environment in each period. The MAPK loop can adaptively change the state of each module in the modules management components based on the MAPK rules and rules defined by the developers in the MAPK rules. The adaptive runtime components is update and shifts to execute the best version of each module. MakeK rules is structures defined by developers of the embedded application that enables JetCert to shift between different versions of each module according to the rules. JetCert facilitates change management by implementing CI/CD pipelines and enables the update process of change for the safety critical systems. JetCert prioritizes change made by developers and ensure that JetCert deploys a higher priority update first. JetCert make it possible to continuously make change over different versions of each module. JetCert creates a priority queue to organize the modified versions, placing each modified version in the priority queue according to a priority level. Finally, Builder is a library in JetCert that performs operating system and infrastructure operation with a high level of abstraction for other JetCert subsystems. Builder has various functions that handle different OS and infrastructure requirements. The Builder subsystem consists of three main components named Safe Builder, Fast Builder, and a CI/CD Builder. As an example, we implemented an safety critical system with JetCert, and we will see its experiment. This system has 4 self-adaptive requirements: user login, cryptography, finance, and physics. As a result, we implemented 4 modules in these systems, each with different versions with unique features. User login module, finance module, cryptography module, and physics module with different versions. For experiments, these graphs show JetCert adaptively to potential attack for 2 modules and in 3 periods, and each period is 16 seconds. When the probability of attacks increase within MakeK period and greater than threshold defined by developers of safety critical systems, JetCert automatically shifts to a more secure version of the module and returns to a faster version when the potential threat is eliminated. These graphs show the time it takes to monitor the environment and decide on the best version for each module. First chart is the process time of MakeK control loop in 100 period, and the second chart is the time to adopt of these 100 periods. These diagrams show the process of making change to the Git and their priority update based on time. The first chart is the number of changed version, modified version over time. The second chart is the processing time and adding to the queue in order of priority based on time. And the third chart is the update chart of modified versions based on time. Finally, this diagram shows all the embedded system pipelines that we implemented with JetCert and shows the shift between different versions of each module under different conditions. The first pipeline is for MAPE and MakeK, and the next pipelines are for modules and CI/CD pipelines. For conclusion and future direction, JetCert is a novel self-adaptive compilation framework designed for embedded and safety critical systems. It can balancing safety and performance at runtime. It can robust adaptively in resource constrained environments, and it has prioritized CI/CD pipeline. And in future, we want to translate off Python subset to concert compatible C code and add RL for update priority decision making in CI/CD pipelines, and we want to have better builders in our framework. So our project is available in Zenodo, and you can clone it. And thank you for your attention.
Okay, even though the author is not here, let's give it up for the author remotely. And let's try to make the online Q&A session. Can we make it or not? Okay, then. Okay, then let's move to the next talk. Okay, the second talk is from the Bingyu Gao from Peking University, and their talk, the paper title is the Group Tuner. So let's welcome the presenter. Yeah.
Hello everyone, I'm Bingyu Gao, a PhD student from Peking University. Today I will present our work, Group Tuner Efficient Group Aware Compiler Autotuning. Compilers provide hundreds of optimization options for users to improve program performance, but the huge number of options and their complex interactions make it difficult for users to fully understand and leverage them. And improper use of options may even degrade program performance. As a result, compilers provide standard optimization levels such as O3, a fixed sequence of options, and can improve performance in general. However, as program features and hardware architectures varies, standard optimization level cannot always guarantee the best performance. For example, the figure shows the performance improvement percent over O3 after random autotuning, and the maximum improvement can exceed 30%. This means that we can find sequences performing better than O3, and this is why we need compiler autotuning. Compiler autotuning can automatically identify better option sequences for specific programs. This figure below shows the autotuning process. The search algorithm begins by generating option sequences and evaluating their performance. And guided by the observed performance differences, the search algorithm iteratively refines its search direction, progressively generating and evaluating new sequences until converging to near optimal sequences. And the key to autotuning is to identify critical options that significantly impact program performance, and then focus the search on these critical options to improve searching efficiency. For example, Boca identifies critical options based on Bayesian optimization and random forest model, and the CFSCA identifies critical options based on program structures and flipping strategy. However, the biggest limitation of the existing solution is that it cannot accurately identify critical options. This is because the search space is sparse and noisy. Existing masses typically change multiple option states across the entire search space in each iteration. As a result, iteration history often contains sequences differing in the states of many options, and there are many redundant options that do not contribute to the performance, making it challenging for algorithms to accurately determine which specific option contribute to the performance improvements. For example, in the following iteration history, these two sequences differ in the states of three options, but in fact, only one option contributes to the performance improvement, and the other two options are redundant, and the program do not have the optimization space for them, such as the option targets at the switch statement to optimize the option that contains no switch statement at all. Moreover, these truly critical options do not independently improve program performance, and it relies on the interactions with other options whose states remain unchanged between iterations, further complicating the algorithm's ability to correctly recognize its importance. As a result, algorithms often mistakenly regard all differing options as potentially critical and subsequently prioritize these options in future searches. Such inaccurate identification of critical options leads to the generation of suboptimal new sequences and ultimately reduce the overall search efficiency. So how should we identify critical options? Our insight is rather than inferring critical options from limited history data in sparse and noisy search space, we directly leverage historically high-performing sequences as a start point in each iteration. As the evaluated high-performance sequences in early iteration have demonstrated their potential effectiveness, they offer a solid baseline from which local adjustments can uncover gains. And since blindly modifying the states of all options across entire search space risks destroying its existing interactions between options and causing performance regressions, we adopt a more controlled approach, restricting the modification of each iteration to a small functionally related group of options, and this preserves the original high-performance structure of the evaluated sequences and can further explore the new potential critical options and interactions. For the same iteration history we showed earlier, Group Tuner directly selects the better performing sequences as a new starting point and only mutates the states of one functionally related options or group of options, for example, loop options. Without explicitly identifying critical options, it explores new critical options while preserving the states of previously effective ones. Even if the algorithm mistakenly alerts the states of critical options, the worst sequences will be discarded in the future, and the search will then continue based on the prior high-performing sequences, ensuring that the overall search direction remains unaffected. Next, we introduce the overall structure of Group Tuner, which consists of two main stages, option grouping and the group-aware mutation search. In the option grouping stage, we organize the options into functionally related groups, and then during group-aware mutation search, Group Tuner performs mutations at the group level based on historically top-performing sequences. The goal of grouping option is to partition the search space to functionally related groups to facilitate the group-aware tuning. Based on the GCC completion process, we can group options according to their relationships with paths. Specifically, options that control the same path or are associated with the same stage can be grouped together. It is because the paths with the same stage usually share similar goals, and the options invoked by the same path have higher probability of exhibiting synergistic effects. Specifically, option grouping has three steps. First, we group options that belong to the same path, and then we merge overlapping groups as certain optimizations, then multiple paths. Finally, we assign ungrouped options those linked to isolated passes to the nearest existing group based on the path execution order to avoid over-fragmenting the space. And this grouping strategy can facilitate the discovery of synergistic effects among related options during the tuning process, thereby improving the overall program performance. Finally, we categorize 200 GCC options into 15 functionally related options, and each group contains 4 to 28 options. And then we design group-aware mutation search process based on the option grouping results. And the core of the group-aware mutation is how group tuner generates new sequences based on iteration history. We first select a top-ranked observed sequence from the iteration history and randomly select one group, mutate the states of the option within the group to generate the new sequence. At last, we can retain original high-performance structure and effectively explore potentially new critical options and their synergistic interaction. And our auto-tuning process includes 2 steps. First, initialization. We use the O3 configuration as the initial start point, as it represents an effective and well-established optimization sequence crafted by compiler experts, and to avoid getting trapped in local optima by relying solely on the best-performing sequence from previous iterations. We perform multiple group-aware mutations on the O3 sequence to generate and evaluate diverse new sequences and add them to a candidate list, serving as start point for the subsequent iterations. Second, we perform history-based search in each iteration. We randomly select one sequence from the candidate list and perform group-aware mutation on it to generate a new sequence. After measuring its performance, if the new sequence outperforms the worst sequence in the candidate list, it directly replaces it. Otherwise, we apply the simulated annealing strategy to decide whether to accept the new sequence, and which helps maintain a balance between the exploration and exploitation and avoids premature convergence. We evaluate the effectiveness of group tuner using GCC9 as the target compiler and set the number of iteration to 500. And our benchmark suite includes programs from Cbench, Polybench, and Spec. The right figure provides the detailed information about the benchmark. And we compare group tuner with 5 approaches: random iterative algorithm, simulated annealing, self-SCA, BOCA, and SR tuner, which the later 3 represent the latest state-of-art auto-tuning algorithms. And our evaluation metric is the percentage improvement in performance over O3. First, we evaluate the performance improvement achieved by group tuner. The figure on the right shows the average performance improvement over O3 for each algorithm on the benchmark set and measured by every 50 iterations. We can note that within 500 Turing iterations, group tuner gets the highest overall performance improvement at 12.38% over O3, up to 3.3% better than others. And we can note that group tuner consistently maintains the highest performance throughout the entire tuning process. Next, we analyze why group tuner can discover better sequence more efficiently than existing machines. The figure on the right compares the performance trend of sequences over iterations for group tuner and BOCA. We can note that the average performance of sequences generated by group tuner is better than BOCA, and there are 3 main reasons why group tuner can be better. First, it fully makes use of iteration history. Group tuner generates new sequences based on top-ranked evaluated sequences, enabling the search to build on past successes. Second, group tuner enhances discovery of better sequences by group-level mutation increase the likelihood of uncovering new critical options and their synergistic relationships. Third, group tuner has better search stability. Although occasional performance drops may occur, group tuner discard suboptimal sequences early, only choose the top-ranked evaluated sequences at the start point, preventing the suboptimal sequences from hindering the overall optimization trend. Next, we evaluate the search efficiency of group tuner. We compare the total time consumed for 500 iterations for each algorithm and define the efficiency as a time ratio relative to random iterative algorithm. The figure shows the efficiency of different algorithms, and we can note that the group tuner is the fastest algorithm, consuming only 77% of the runtime required by random iterative algorithm. Conversely, methods such as the FCA and VOCA, which retrain prediction models using updated historical data in each iteration, exhibit significantly higher overheads, and this prohibitive tuning overhead severely limits their usability. And we also evaluate the performance of group tuner on other GCC versions, such as GCC 11 and 13. The results show that group tuner can still achieve better performance, demonstrating its effectiveness. In conclusion, we propose group tuner, a group-aware auto-tuning algorithm that functions the search at the group level. And the group tuner can achieve the best performance improvement compared to SOTA methods with an average speed of 12.39% over O3, and it is also the most efficient, requiring only 77% of the time required by random search algorithm. And this is all for our presentation. Thanks for listening. We are happy to take any questions.
Okay, let's give it for review first. And please raise your hand if you have any question or comment. Yes.
Thank you for a great talk. Actually, I was author of the SR tuner. Actually, I was so sad for that. The SR tuner shows the lowest performance in the evaluation. But anyway, it is a really good job. My question here is that your work looks really good, but do you think if this work achieves the theoretical maximum performance, or close to that, or if not, which opportunity do you miss?
Sorry, can you?
My question is that, what do you think about your performance gain now? Is it close to the maximum or not? Is it still far from the maximum performance we can get?
Actually, we may never know the maximum performance improvement because the search space is too big, too huge. But actually, we do experiment with longer iterations, such as our evaluation is 500 iterations, and we test 1,000 iterations further, and the improvement can be higher. Yeah, so if we have enough computational resources, the performance improvement may be higher. So it still has a gap between the maximum performance improvement. Thank you.
Is there any other question or comment? Actually, I have a question. So you show the list of the group, and is there any automated methodology to group these things?
Actually, it's a difficult problem, and it is because the completion process of GCC is complicated, and it have been updated over years, and the computation process is complex, and we do not have a clean and beautiful strategy to automatically grouping them. But we have tried our best to find their commons, and we find that the options within the same path has the higher probability to have the close relationships. So this is our solutions.
Thank you for your answer. Is there any other question? Actually, I have a follow-up question, so if I can spend more time, then I have a more question. So you show like the great experimental result, and you explain why your work outperforms like Professor Park's works as a tuner, and you beat him. Actually, my question is, depending on the target processor, your like auto-tuning methodology shows like the variety in performance. Have you observed that phenomenon, or can you explain further about your like the performance variability in depending on the target performance?
About why it is better?
Or like, is it working on like the different type of the processor? That's my question.
We just evaluation it on the LCTES processor. Yes, this is our computational.
I'm not rushing or giving you some pressure, because like nowadays China is developing a lot of CPUs and processors. So I'm just asking if you have some more experimental results on with the processor in like the manufacturer in China. That's the thing. Yeah.
No, we did not evaluate it on other CPUs, and it because the experiment is quite time consuming.
Yes.
Yes, it makes consume over 1 week to complete the work. Yeah.
Okay, this is a really great work, and thank you for your presentation. And once again, let's give it for Mingyu. Thank you very much. Okay, now we have the third talk. Ju-hyung is from Ju-hyung. The title is Multi-Level Machine Learning Guided Auto-Tuning for the Efficient Code Generation on a Deep Learning Accelerator. The Ju-hyung is from the Korea University of Science and Technology, and this paper is in a collaboration with the ETRI, which is the National Research Center in Korea.
Can I start this presentation? Okay. Thank you. Good afternoon, everyone. Thank you for attending my presentation. My name is Ju-hyung Cha. I'm currently pursuing my master's degree at University of Science Technology, working in collaboration with ETRI. This research is a joint work with my colleagues from ETRI. In this presentation, we'll proceed to follow others: motivation, system architecture overview, methodology, evaluation, and summary. Let me start with some background. In recent years, the demand for deep learning inference on embedded systems has grown significantly. We can see a wide range of applications, including object detection, facial recognition, autonomous navigation, and even generative AI, like real-time translation. All of these require AI model to run efficiently and reliably on embedded system. On the hardware side, the landscape is also very diverse. Each platform comes with its own constraints in terms of memory, computer power, and cost. As a result, there is a growing need for multi-dimensional optimization, not only to maintain inference accuracy and speed, but also to reduce development and deployment costs. Now, let's talk about auto-tuning, which is one of the key optimization approaches used in deep learning compiler. In this context, we can assume that the algorithm is fixed and the hardware is fixed. That means the what and the where is already determined. But here's the key. For deep learning operations, depending on how these are scheduled, performance can vary significantly. While compiler or library can decide how to run the computation, there's no guarantee that they will find the best possible schedule. This is where is auto-tuning coming. Auto-tuning automatically generated a search space of possible schedule for a given algorithm and tries to identify the most optimal one, so profiling or predictions. For our auto-tuning experiment, we used VTA, a deep learning accelerator developed under the Apache TVM project. VTA has a very simple architecture consisting of three main modules: load, store, and compute. As shown on the right, there are three purposes: input, wait, and output. And all modules can operate in parallel, enabling pipeline execution. Despite its simplicity, VTA shows high performance and offers significant flexibility in buffer allocation and scheduling. This high degree of freedom and modularity is exactly why we choose VTA as a target platform for evaluating our auto-tuning technique. Like other processors, VTA also has refined performance models. Depending on the algorithm we run on the VTA, its arithmetic intensity can vary, which directly affect whether the computation is compute-bound or memory-bound. Schedule tuning enables a wide range of execution strategies, and depending on how we schedule the operations, the performance of the same algorithm can vary significantly. One simple way to schedule computation on VTA is to create a virtual thread. First, the thread allocates on J buffers for input, wait, and output. Then, it loads input and wait from the DRAM into the buffers. Once the data is loaded, it computes the matrix multiplication. Step 2 and 3 repeat multiple times. Finally, once all computation is done, the result is back to the DRAM. One of the tuning knobs that can improve utilization is tiling configuration. By adjusting the buffer allocation size and amount of computation per tile, we can potentially optimize utilization as illustrated in the diagram. The Second tuning knobs is virtual thread configuration. By creating multiple threads, each with independent purpose, we allow different modules to run at the same time. The overlapping execution helps to hide memory latency and improve overall hardware utilization. The typical auto-tuning process is iterative and consists of several steps. First, the system uses a cost model to predict the performance of different configurations. Then, it compiles best candidate configurations and runs them on the target hardware. Based on the measured execution times, the cost model is retrained, improving its prediction accuracy over time. By repeating this process, the custom model gradually learns to make high accurate prediction, which helps the tuner identify to find the best configurations. To train the custom model, we use input features, which typically include the tuning knobs and measured execution times. For VTA, as mentioned earlier, the main tuning knobs are tiling and virtual thread configuration. Tuning knobs introduce a large search space of possible configurations. There are countless ways to set tile size, thread count, and memory layouts. But more importantly, many of these configurations turn out to be invalid, either due to hardware constraints like limited purpose size, timing mismatch, or illegal memory access patterns. This can lead to purpose allocation failure and runtime errors. In the worst case, an invalid configuration can crash the hardware and force a system reboot. All of these errors can lead to significant delay in the tuning process. To address these challenges, we propose a multi-level machine learning guided auto-tuning technique. In addition to the existing custom model P, we introduce two more models. Model V, which predicts whether a configuration is valid or not, and Model A, which provides a more accurate prediction performance by leveraging hidden features. As a result, this addition allows us to find better performing code much faster. Now, I will explain how multi-level machine learning guided auto-tuning solves the problems we had before. And let's look at each step. Just like in typical auto-tuning, Model P suggests configuration that it thinks will perform fast, but many of these configurations turn out to be invalid. To solve this, we add the next step, Model V. Model V is a classifier that checks whether a configuration is valid before we compile it. By filtering out invalid configuration early, we can skip unnecessary compiles and measurements. This also reduces the number of tests on the target hardware and helps prevent crashes. As a result, the system becomes more stable. So in the end, only possible configurations can proceed to the compile stage. The compile process is a series of analyses and decisions to better predict the performance of generated code. We add a hidden feature extractor inside the compiler. This extractor collects extra features, example hidden features, during compilation. These include metadata related to things like memory allocation and parallelism. Newly added model A also predicts the performance of each configuration, just like model P. But model A uses extra hidden features collected during compilation. Because of that, it can make more accurate prediction than model P. By adding this extra filtering step right before evaluation, we improve the accuracy and reliability of the auto-tuning process. We implemented on VTA. VTA is Xilinx ZCU102 FPGA board. To support this, we also developed a backend compiler using PyTorch glove. For training the custom model, we used XGBoost. We ran experiments using the well-known neural network, Resonance 18 and Extension V3. Next, we show the experimental result on 3 layers of Resonance 18. The orange bar shows our method, and the blue bar shows the baseline method. The top graph shows how many code samples were tested on hardware, and the execution time of the best code. Our method finds better performing code using fewer samples. More importantly, the bottom graphs show the invalidity ratio. Our method reduces invalid configuration by more than 60%, which means a big reduction in tuning time. Also, the histogram shows that our custom model finds high-performance configurations more effectively. Injection V3 uses uncommon corner filter shape. This makes it more likely to produce invalidity ratio. But our method shows a low invalidity ratio and performance auto-tuning effectively. This experimental show whether extracting hidden features and using model A for another prediction is valuable. Model A has more than 10% lower root mean square error on average compared to model P, showing it makes more accurate prediction. We conducted comparative experiments across all conversion layers in Resonance 18, and the detailed results can be found in our paper. We propose a multi-level machine learning guided technique to solve hardware error and address the limitation of existing features during the auto-tuning process. We summarize all of our experiment results. First, by employing the validity checking model, we significantly reduce the invalidity ratio. Second, by extracting hidden features from compiler and using hidden features to predict performance, we can reduce average prediction loss by about 10% per layer. Our method can significantly reduce invalidity ratio and configuration and improve conversion speed. Thank you for listening to my presentation.
Okay, let's give it for Juyong. Is there any comment or question? Yes.
Thank you for your great talk. I think the key difference from existing autotuning is the use of hidden feature, but I didn't fully catch what that actually means. So could you briefly explain the what hidden feature are and how they are extracted?
Oh, okay. I'm already ready back up for describe hidden feature extractor. Hidden feature extractor is work like a variable create and deliver event in compiler and capture a variable value in this list. First and to for loop count and in a loop variable value and if condition value in if statement. So all of this work on this sequential. We are corrected value in hidden features.
Okay. Does it answer your question? Okay, got it. Okay, is there any other question or comment? Yes.
I have one question. So basically the VTA is a really simple MPU actually, and you are working on the autotuner in the TVM. Okay, and basically I think the autotuner of the TVM is really good, and you upgraded the autotuner, and I think the autotuner of the TVM is good for targeting the GPU. So can you apply the advanced mechanism to the GPU or not?
Oh, not yet. This algorithm to GPU test on this algorithm. Oh, not yet tested on the GPU, but more expansion experiment. I will try this on test on the GPU.
So do you think you will this work will be
Yes,
will
maybe.
show the better performance even for the GPU? Correct?
Yes. Maybe maybe GPU has not many errors, not many errors, so not will work.
So you're saying is that the good thing for your work is to avoid the compilation errors.
Yes.
That kind of okay, I got that.
Thank you. Is there any other comment or question? Please raise your hand. Okay.
I got that you sort out invalid configurations, but I was wondering, maybe you said it, but I didn't get it. Are there any false positives there that you sort out configurations that are actually valid? Like maybe you think in your program that one configuration is invalid, but it actually isn't. Can this situation happen in your work?
Your prediction may be correct, but sometimes not. So do you see something mistakenly happen in your implementation?
Oh, this model free is validity check model is work on deep learning model based on. So this validity check model it likely same to errors make problems because first time model free is not well known the error information make not very check work. So after long time and after a long time
it's okay. So I can translate a little bit because he said if mistakenly like choosing a decision happened, then after a long time, then if the code, while the code is stabilizing, that thing is also considered as an error, so we can compromise it over and over. That's what he's talking about.
Thank you.
Okay, time is up, so let's give it for the presenter once again. Okay, the last talk in this, oh my gosh. Last talk in this session is the DSP and MLIR, so which is from the, Aribal from the Arizona State University. Okay.
Haha. Thank you. Hello, everyone. I'm Kyung from Yonsei University. I'm the session chair of the last one in LCTES 2025. I know, if you look at outside, it's beautiful, even though it's a little bit hot. But after the session, probably you can, explore the beautiful sites, shops, restaurants in Seoul and Korea. So that means I like to make it quick, but very interesting, okay? I think we have 4 presentations, but first 2 are pre-recorded, and the last 2 will be presented. But I don't know why this one is large bold. Okay, let's get started. The first one is Alvisor, and this one is from Arizona State University and University of Novi Sad. Can you start? All right.
Hello everyone, my name is Edwin Kayang and I'll be giving a presentation on Alvisor, an extensible dynamic binary analysis and instrumentation tool for open instruction set architectures. To begin, within the domain of software engineering, binary instrumentation is a very useful technique. So this involves inserting some additional code termed as instrumentation routines into the binary. And we can do this for multiple use cases. For example, we can use it to profile a binary and identify the various bottlenecks. And then once these are identified, we can apply various optimizations and improve the performance of our binary. We can also use it to identify bugs within the binary and patch these bugs. And that falls within the realm of software debugging and testing. So there are 2 ways to go about binary instrumentation. The first one is the static method, and this produces a new binary containing all the instrumentation routines. Alternatively, we can do dynamic binary instrumentation where we execute the binary and make the changes at runtime. So as such, no new binary is produced. And this dynamic method also allows for more fine-grained control over the instrumentation process. Binary instrumentation is a mature field with over 20 years of development, and within the landscape of binary instrumentation, there have been multiple tools developed, for example, Intel Pin, DynamoReal, and Valgrind. However, a common trend is that initial versions of these tools are built to support specific architectures such as x86 or ARch. And based on the instruction set architecture that these architectures use, they are classed as closed ISAs. That is, they are bound by restrictive licenses, preventing third parties from being able to develop new extensions or instructions on top of these architectures. And what this means is that if any tool is being developed for such an ISA, there wouldn't be a hard requirement for extensibility. And so if a new extension were to come up in such an ISA, what that will mean is that a user would have to go into the code base of the binary instrumentation to search for all the locations that need to be changed in order to account for this new extension and then make those changes manually. Now to do this, the user would need to have a deep understanding of how the tool works. And if the changes are not made correctly, you could end up introducing bugs into the tool which would taint the correctness of the instrumentation process. This problem becomes more serious when we consider the rise of open ISAs in our modern times. With open ISAs, their main selling point is their non-restrictive license, which means that third parties are freely able to develop instructions or extensions which can help accelerate workloads in various domains. And in reality, new extensions are actively being developed for these ISAs. So for example, if we take RISC-V, one of the popular open ISAs, you'd find out that in 2024, they ratified 15 new extensions. And if we look through the publication history, you'd see that a lot more extensions were developed for them, although these extensions have been unratified. And when we consider all this, it brings about a new requirement for binary instrumentation tools for such architectures. And that is, the binary instrumentation tool needs to be extensible to account for the new extensions that are developed for such ISAs. And that brings us to our problem statement. So these existing binary instrumentation tools were not developed with the extensibility feature as their core requirement. And what that means is that if the underlying ISA releases a new feature, then developers would have to go into the tool's code base and manually make changes to support the new ISA feature. And so this can be a very laborious and intensive process, and it can also introduce bugs that would end up tainting the correctness of the instrumentation process. So to solve this, what we need is an extensible binary instrumentation tool. And if done correctly, it will enable the tool to more easily be able to keep pace with these evolving open ISAs. To solve this problem, we present RVisor. And RVisor is an extensible dynamic binary instrumentation tool which we have built to solve the extensibility needs for open architectures. And we focus on certain features such as the low overhead so that it would be useful in most instrumentation use cases. And we also give it a just-in-time based execution model for instrumenting the binaries. Additionally, we include a flexible instrumentation API which would allow users to write custom routines. So to solve the extensibility aspect, we make use of the RVisor domain-specific language. And so RVisor uses the RVisor DSL to specify the various new ISA features, and once these have been specified, they will be automatically integrated back into RVisor for users to instrument while accounting for these new ISA features. Now let's take a look at the architecture of RVisor. So first off, we start with a target binary, which is an ELF binary, and we send that to the ELF parser, which extracts the relevant segments from the binary. Next, the code gets sent to the decoder, which translates it into an interpretable form for the rest of the tool. Then we segment our binary into traces using our basic block allocator. So for the purpose of RVisor, traces first start off as basic blocks, and these are stored in the code cache while keeping track of the locations of the various traces. Next, we have a dispatcher which manages the control flow within the code cache. So once a trace completes execution, control switches to the dispatcher, and the dispatcher must select the next trace to be executed on the hardware. Finally, we include an instrumentation API which allows users to write their routines as custom C functions. And it also allows them to specify when the routine should be called during execution. So traces are one of the areas where we had to make a lot of design decisions for RVisor. And so within the context of RVisor, we begin each trace as a basic block. And since after the trace executes, we need to return control to the dispatcher, what we do is that we include a stub at the end of each trace. So the stub contains code to trigger a context switch routine, and that enables us to return control to the dispatcher. Now, another consideration we need to make with respect to our traces is that we need to ensure that they run with minimal overhead. So that's in terms of both execution and memory. And so we use certain optimizations to achieve this. The first of these optimizations is termed trace linking. And what this allows us to do is that we're able to connect two traces to each other within the code cache without the intervention of the dispatcher. So it helps reduce the number of context switches between RVisor and the code cache, which would reduce the execution overhead. We also include a second optimization known as stub regions. So since the stub code is similar for most traces, what we are able to do is that we store the stub code within a centralized location inside the code cache, and we terminate each trace with a jump instruction to that stub region. So this effectively reduces the amount of stub code that we place within the code cache and reduces the total memory overhead of RVisor. So now that we have the architecture set for RVisor, the next thing we need to consider is the extensibility aspect. So to do that, we need to look at the various components and their different requirements for extensibility. For example, the decoder and encoder need an understanding of how each instruction should be broken down into its subcomponents. The basic block allocator would need to understand the various control flow instructions within the ISA, and the instrumentation API would need an understanding of the registers and instructions so that it can relay this information to the user for use within the instrumentation routines. Now, in any traditional tool, if there's any ISA change, this has to be specified within the source of the underlying binary instrumentation tool. However, we can help automate this by using a DSL where we can concisely specify the various ISA components, and these can be integrated back into the tool. And we're able to achieve this using ArchVisor. Now, ArchVisor is a source-to-source domain-specific language which we use to integrate these new ISA features back into ArchVisor. So first off, we start by writing the ArchVisor sources, and we pass these to a code synthesizer which is able to generate extensions within the source language of ArchVisor tool. And these two are compiled together to produce an ArchVisor binary which can be executed together with the target binary to produce our instrumentation output. To design ArchVisor, the first thing we need to consider is the grammar. And in our case, we're going to look at the various components of the ISA that we need to specify. So for our initial version, we look at the instructions, the registers, and we also consider the instruction types, since these control how an instruction should be encoded or decoded. After considering these, we're able to develop ArchVisor to have three different data types. The first is the instruction type, or int type, which specifies the various components of each instruction and their locations within the binary instruction. And then next we use the instruction type to give specific values to the various components of the instruction. And finally, we have the reg file type, which specifies the various registers within a register file together with their load or store instructions. And this helps us with the context switching process. We implemented ArchVisor in roughly 8,000 lines of C code while using custom versions of certain libraries and data structures. For example, with the elf parser, rather than using a library like libelf, we used the deploting process to strip down the amount of code that went into the final version of ArchVisor. And ArchVisor currently supports RISC-V, specifically the RV64 GC toolchain, as this is a general toolchain for most workloads. Finally, we have an ArchVisor backend created specifically for ArchVisor, and this supports features such as the custom instruction groups, which can be used as target points during the instrumentation process. To evaluate ArchVisor, this is the experimental setup we consider. First off, the hardware consists of a trireme RISC-V processor hosted on an FPGA, and then for our operating system, we use a minimal busy box hosting a Linux kernel. Then to evaluate the performance of ArchVisor, we consider the EMBench benchmark suite, which is made up of about 23 binaries for deeply embedded systems. Then to compare our performance of ArchVisor against state-of-the-art tools, we compare ArchVisor against DynamoRio, which is an industry standard dynamic binary instrumentation tool that had a port developed for RISC-V in 2024. Finally, the instrumentation routines that we evaluate on are the no instrumentation routine, where we just consider the execution overhead of running the binary with the instrumentation tool. And we also look at the basic block counting routine, and this routine dynamically executes the binary and counts the number of basic blocks that were executed. So first off, we look at the comparison of the execution overheads of both ArchVisor and DynamoRio, and using both the no instrumentation and basic block counting routines. And in both cases, we see that ArchVisor is able to maintain a lower overhead. And if we look at the basic block counting example, we can see that ArchVisor is able to have a more minimal increase in overhead as compared to DynamoRio. And this trend continues when we look at the memory overhead comparison. Moreover, ArchVisor is able to maintain consistently less overhead across all the binaries that we tested on. Then to compare the overhead of ArchVisor, we look at the number of lines of code required to support certain extensions in both ArchVisor and DynamoRio. So in this case, we used the floating point and compressed extensions, as these are available already in DynamoRio. And in both cases, we can see that there's a substantial reduction in code needed in ArchVisor to support these extensions. And this goes to show the usefulness of ArchVisor in achieving the extensibility within our binary instrumentation tool. Next, we move on to our use case, which is instruction emulation. And this can become useful when we have hardware support for certain ISA features, but we don't have that same support in the compiler. So in this case, the hardware supports compressed instructions, but the compiler cannot support compressed instructions. So we need an instrumentation routine that will be able to translate the uncompressed instructions to their compressed versions. To provide this support, we need to first create our ArchVisor sources, and these are going to consist of the instructions that have the compressed equivalent. And as you can see, we're assigning these the DBT group to help us with the instrumentation routine. And then once we've declared all of these instructions, we declare their compressed equivalent so that we can translate from the uncompressed to the compressed format. Next, within our instrumentation routine, we start by using the routine to match the various uncompressed instructions and replace them with their compressed equivalent. Then within our main function, we invoke the instrumentation routine whenever we encounter the DBT group, and this helps provide lower overhead than us running the instrumentation routine on every instruction that we encounter. So on executing these benchmarks on the EMBench suite, we're able to get an average size reduction of about 16.94% after we translate the uncompressed instructions to their compressed format. In the future, we want to look more towards making ArVisor a more comprehensive tool. And what this would look like is adding support for more advanced program features such as multi-threading, self-modifying code, and dynamically linked libraries, as these are features supported by a lot of general purpose binaries. And we'd also want to look at handling OS level functionality, privileged functions such as context switches and interrupts to make it be able to instrument more comprehensively. Then within the realm of ArchVisor, we want to look at extending it to do things like allowing the creation of instrumentation routines directly within the ArchVisor sources rather than using a separate language. And we also want to look at integrating ArchVisor into other areas of system development, for example, hardware simulations. In conclusion, within this presentation, we have looked at ArVisor, which is an extensible, just-in-time based binary instrumentation engine that we have built specifically for open ISAs, and it makes use of the ArchVisor domain-specific language, and that helps it to achieve the extensibility and solve the problem of extending traditional binary instrumentation tools. And this DSL allows it to provide a concise way of integrating the new ISA features back into the ArVisor tool. Within our evaluation, we are able to show that ArVisor has low runtime overhead, memory footprint, and code overhead. Finally, the ArVisor tool is open source and made publicly available under an open source license. I would like to thank the organizers of LCTES for giving us the opportunity to present our paper during this conference, and I'll be available to answer any questions concerning the work. Thank you.
Are they online? Yes, then let's take questions from the audience. No questions, no comments? Please.
First off, thanks for the talk. I noticed that there is a strong parallel between the architecture of a tool like Kimu and ArVisor. Have you looked at all the crazy optimizations they do to make everything as fast as possible?
So we haven't looked at the optimizations related to Kimu specifically, but we've compared the optimizations to other dynamic binary instrumentation tools, so more mature tools. And so we do borrow some inspiration from the optimizations they implemented. For example, we implemented similar versions of their methodology for the trace linking.
All right, thanks.
Any questions? Okay, then let's thank the authors and presenters. Thank you. Okay, our next talk is also pre-recorded. Okay, let's get started.
Hello everyone, I'm Aobo Yang from Southwest University. I'm delighted to present our work ZMP today. This presentation has 4 parts, and let's start with the background and motivations. SSD is widely used in computing systems thanks to the advantage of high read and write speed, high reliability, and lower power consumption. To efficiently manage SSD and exploit their performance potentials, an SSD is generally organized into 3 key components. The host interface is responsible for communicating with the host systems. The SSD controller is responsible for managing flash memory. More importantly, SSD are composed of numerous parallel units and offer multiple levels of access parallelism to improve SSD performance. For the parallelism of channel and chips and dies have been well exploited, whereas plan-level parallelism is achieved through advantage multiplan operations and remains subject to constraints. This figure illustrates the current structure of a flash memory die. As depicted, the memory cell area are grouped in 2 planes. Each plane has a private page buffer, allowing it to operate independently. However, the peripheral security, which serves only one page address at a time, is shared among all planes, as shown in the figure. Therefore, plan-level parallel operations are only allowed when the page address of planes have the same offset. This limitation inherently hinders the full exploitation of plan-level parallelism. Therefore, to overcome these limitations, some studies propose opening a group of blocks with the same offset across different planes to server requests, thereby improving plan-level parallelism. However, maintaining multiple active blocks simultaneously can lead to the open block issue. Next, I will introduce the concept of the open blocks. The figure illustrates the structure of an open block, which contains both programmed and unprogrammed word line. Specifically, programmed word line cells are injected with electronics to store data, whereas unprogrammed word line cells remain in the erased state without electronics. Meanwhile, a vertical column of storage units is referred to as a string, and the storage layer is shared by all memory cells within the same string. If open blocks are not fully programmed within a short period, charge leakage may occur in the memory cell, which can lead to a higher error rate. The figure shows the electronic distribution within a net string. Due to incomplete block programming, a significant potential difference exists between adjacent word lines, leading to lateral charge migrations (LCM) within the storage layer, which in turn affect data reliability. When the potential difference between adjacent storage cells becomes substantial, LCM become more obvious, especially between the programmed and unprogrammed word line. Furthermore, as the block remains open for a longer duration, the likelihood of read error increases accordingly. Therefore, to quantify the degree of plan-level parallelism utilized in the real-world applications, and to evaluate the impact of open blocks on error rates, we conduct a series of motivation experiments. First, the left figure shows the rate of multiplan operations triggered. As illustrated, the proportion of multiplan operations remains below 0.06% across different workloads, indicating that conventional L scheduling rarely triggered multiply operations. This suggests that the utilization of planar parallelism in the real-world application is significantly limited. This limitation stems from two key factors. On the one hand, it is related to the aforementioned background, while strict optional constraints hinder the tracking of multiply operations. On the other hand, we observe that one-page requests dominate the workloads, as shown in the right figure. A one-page request refers to a request that is less than or equal to the size of a single physical page. Since multiply operations require parallel execution of multiple requests, such request patterns fundamentally prevent multiply operations from being tracked. Second, we collected the number of bit arrows on different one lines within the open blocks and on the varying open ties. As shown in the figure, for each one line, the bit arrow rate increases as the block remains open for a longer duration. For one line with high arrow rates, time-consuming ECC correction is required during reads, which significantly impacts data read latency. In addition, we observe that the last programmed word line exhibits highest error rates. This is because they are adjacent to the unprogrammed word line, resulting in the largest potential difference, which aggravates the later charging migrations. Third, we collected the number of incoming requests over time. As shown in the figure, it is evident that request arrival rate varies significantly across different time intervals. This observation suggests that workload changes should be taken into account when addressing the problem. In summary, we aim to address three key challenges. To track these issues, we propose setMP, and let me introduce the execution flow of setMP. First, there are three one-page requests, and they are typically distributed across different parallel units based on their logical address through conventional mapping. However, due to the lack of the cell-wide offset across blocks and the limitation presence of multiple requests within the same die, it is difficult to track MP operations. To address this, setmap first group multiple channels into a set. Within the set, setMP operation an additional group of MP blocks on the selected channel. Where the block shares the same wide offset, is then check whether the set contains sufficient one-page requests that can be gathered to trigger multiply operations. If so, these requests are reassigned to the MP blocks. When an MP block becomes full, setMP determines whether to increase or decrease the number of MP blocks in order to control the block open time. Finally, since requests may be reassigned across channels within a set, setMP maintains additional flag bits in the mapping table to record the updated physical location. The above approach efficiently addresses the challenge identified earlier. In the following, we discuss several design details. The composition of a set refers to the number of channels grouped into a set. Since request redistributions occurs only within a set, a small unset implies fewer candidates for redistributions, potentially resulting in fewer multiply operations. For example, If a set constrains only 2 channels, the available requests for redistributions are limited to these 2 channels, which may not be sufficient to trigger multiplying operations. In contrast, with 4 channels in a set, more candidate requests become available, increase the likelihood of triggering multiplying operations. However, a large unset introduces additional mapping overhead as shown in the formula, and increase the complexity of request scheduling. Closely related is the composition of unstep, which donated the interval between channels when forming a set. As illustrated in the figure, when unstep equals 0 and the workload is heaped stronger spatial locality, the load tends to concentrate on a set edge set 0, while other set edge set 1 remain lightly loaded despite the intracted inset request redistributions. In contrast, when a step equals 1, requests are more evenly distributed across different parallel units, resulting in better load balancing and improved performance. Therefore, we recommended using a large step size to achieve more efficient request distributions. Another important component of set MP is MP block adjustment. When an MP block becomes full, set MP triggers an adjustment process. It first compares the number of incoming requests in the most recent time window with the average value of the previous window. If the differ is positive, it indicates a higher load phase and serves as a prerequisite for opening an additional group of MP blocks. Otherwise, one group of MP blocks is reduced to avoid prolonged block open time. Furthermore, set MP compares the open time of single blocks TAVG and MP blocks within the set. Only if the MP block open time is shorter than that of single blocks will a new MP block group actually be opened. Through this approach, ZMP efficiently controls the block open time while adapting to workload variations. We conducted a set of experiments to evaluate our proposed approach implemented in the MQC simulator. The table on the left lists the SSD configuration parameters, where unset is set to 4 and unstep is set to 3. The table on the right summarizes the workloads used in our evaluation, which are collected from MSR, LUN, and Alibaba trees. There are 4 evaluated measures. First is baseline and PLDI'25, HSAP, and set MP or proposed set associative mapping management schedule for multi-plan optimization. In the evaluated result, we highlighted 4 main findings. The first is the multi-plan operation tracking ratio. Since HSAP purpose maintains aligned blocks, it achieves more multi-plan operations compared to baseline and PLDI'25. More importantly, ZMP improves multi-plan operations count by an average of 65.7% over SHAP. This improvement is attributed to the set associative mapping strategy, which allows more wide requests originally mapped to the different channels within the same die to be grouped into aligned MP blocks, thereby enable more MP operations to complete the request efficiently. The second result concerns L response time. In the figure, the y-axis represents normalized L latency, while lower value indicate better performance. As shown, CMP achieved the lowest latency across all workloads. The third result focused on block open time. The figure presents the cumulative distribution function of block open time on the different approach. As observed, baseline and PLDC achieve the shortest block open time, as they each maintain only a single active block per plane. In contrast, both HSAP and CMP introduce multiple active blocks, lead to relative longer open times. However, unlike HSAP, which opens multiple blocks blindly, CMP employs adaptive MP block management and generally achieves shorter block open time than HSAP. To verify that the number of MP blocks dynamically changes with varying workload conditions, we collected the number of MP blocks in the system over time. As shown in the figure, it can be observed that the number of MP blocks changes continuously, indicating that CMP efficiently adjusts MP block allocation in response to workload dynamically. Finally, let me conclude this work. We propose a set structure to manage multiple DAS across different channels as a group to efficiently exploit the plane-level parallelism. We adjust MP blocks by detecting load variations and comparing active blocks open times to deseated, whether to create a new aligned block pair. We conduct trace-driven simulations tests to demonstrate the effectiveness of our proposed approach. Thank you for your time. If you have any questions, I'd be happy to answer them.
Are they online? Okay, all right. Any questions, comments? No questions, no comments. I have a quick question. If we go to the slide number 23, can you go back to 1 second? Abo, can you hear me? Hello, can you hear me, Abo?
Okay.
Oh, it's quiet. It's quiet.
Hello. Okay, I can hear you.
Okay, sounds good. If you go to slide number 23, I guess.
Hello.
Okay. Slide number 23, I guess. Yes. One of your motivations says, longer the block open time, the reliability is not good, right? And your proposed set MP shows the block open time reaches later as compared to the existing techniques like PLDC and HSAP, right? According to this evaluation.
Yeah.
Can you tell us a little bit about,
because the baseline and the PLDC open one block in the plane simultaneously, but the HSAP and the CMap, they open much open block in the planes.
Okay. Thank you for your answer, but probably I'm gonna send a question via email to to get some the answer. All right. Anyway, thanks again. Thank you. All right. Let's move on. We are a little bit behind. So original schedule. The next one is Lucy. It's going to be presented by Professor Srivastava again. Please welcome Aviro.
Thank you for a kind introduction. I'm Sang-won Choi from Korea University. I'm happy to present our work called Cubism, Disassembling and Reassembling K-means Clustering for Mobile Heterogeneous Platforms. K-means clustering is a cornerstone of many data analysis applications in embedded systems. K-means clustering involves distance calculations between numerous data points and centroids over multiple iterations. This behavior makes the clustering process highly parallelizable. Also, prior work has proposed In양 K-means clustering algorithm to reduce the computational workload. This algorithm identifies and skips unnecessary distance calculations that do not affect the clustering state. This figure shows a simplified example of In양 K-means clustering. At the start of an iteration, data points are clustered into two clusters. For each pair of data point and centroid, the algorithm first determines if the distance calculation is skippable. If the calculation is not skippable, the algorithm performs computation. After the distance calculation, the algorithm reassigns clusters based on the calculated distances. However, running In양 K-means clustering on embedded systems faces two significant challenges. First, the skipping mechanism incurs warp divergence, thus underutilizing GPU resources. Also, existing algorithms do not utilize CPU for distance calculation, which account for most of the execution time. So our goal is to efficiently utilize both CPU and GPU to address these challenges. With this objective, we propose Cubism, designed to improve hardware utilization and overall performance. The presentation is organized as follows. First, I'll explain the motivation of our research and introduce our solution, Cubism. After that, I'll present the evaluation results and finish the presentation with our conclusion. K-means clustering offers high parallelization opportunities, and this figure shows how a GPU performs distance calculations in parallel. Each GPU thread handles one data point and sequentially calculates distances to every centroid. However, with the skipping mechanism, only a few threads within a warp performs distance calculation while others wait. This behavior is known as warp divergence. And this figure shows an example of how warp divergence occurs. In this example, there are 4 data points and 5 centroids, and 4 GPU threads performs distance calculation in parallel. And for the first centroid, each GPU thread checks if the distance calculation is skippable. In this example, only thread 1 performs distance calculation while others wait. Similarly, for the second centroid, only thread 2 performs computation while others remain inactive. The algorithm repeats this process for all subsequent centroids. As a result, a GPU suffers from severe warp divergence. And we provide the number of active threads within a warp during the clustering process. This metric represents the average number of threads that actually perform distance calculation within a warp. So the maximum value is 32. This table shows a ratio of skipped distance calculations and number of active threads and the portion of inactive threads within a warp for 5 iterations. For the first 2 iterations, 91% and 60% of threads remain inactive respectively. Since these iterations have relatively high skip ratios, a GPU suffers from a significant warp divergence. Also, embedded systems can further leverage this parallelism by utilizing CPUs. By collaboratively using CPU, a system can reduce the computational workload assigned to the GPU. And the architecture of embedded platforms also provide advantages. In these platforms, CPU and GPU physically share a device memory. This structure eliminates the overhead of explicit data copy between CPU and GPU. Therefore, a parallel execution of k-means clustering using both processors is a promising approach for acceleration. However, existing algorithms do not utilize CPU for most of the execution time. These algorithms only utilize CPU for a limited number of tasks, such as kernel launch and cluster assignment. Our profiling results show that CPU remains idle for 90% of the end-to-end execution time. These observations show that existing k-means clustering algorithms inefficiently use the hardware resources of embedded platforms. Now I'll introduce our solution, Cubism. Cubism consists of three main stages called clustering reordering, warp balancing, and task distribution. Let me explain these techniques step by step, starting from the clustering reordering. And this figure shows the original Inyan k-means clustering algorithm. This algorithm iteratively checks if the calculation is skippable and then performs computation. In contrast, Cubism first identifies all skippable distance calculations before the computation. Through this process, Cubism can proactively determine the skip ratio and gather information about which distance calculations are necessary. Cubism uses this information to guide the distance calculation phase. In this phase, Cubism employs two core techniques called warp balancing and heterogeneous platform-aware task distribution. During the early identification of skippable calculations, Cubism generates metadata as shown in the left figure. In this metadata, rows represent data points and columns represent centroids. And for each element, 1 indicates the necessary distance calculation and 0 indicates the skippable distance calculation. And each thread uses this metadata to fetch the index of centroid required for distance calculation. And then thread perform only necessary distance calculations, making all threads within a warp actively compute. Similarly, for the next step, each thread fetches the next index of centroid required for distance calculation and then performs computation. Through this warp balancing, Cubism increases the number of active threads within a warp and accelerates the distance calculation phase. This warp balancing technique is effective in iterations with high skip ratios. However, if a skip ratio is low, warp divergence has a minimal impact on performance, and the overhead may outweigh the benefits. To address this challenge, Cubism incorporates a dynamic skip ratio decision technique. First, Cubism sets a threshold of skip ratio where the warp balancing is expected to be beneficial. This figure shows how Cubism sets this threshold. Before the computation, Cubism first predicts the execution time of current iteration, and Cubism uses the skip ratio and the execution time of previous iteration along with the skip ratio of current iteration. This approach relies on two insights. First, the execution time of an iteration is proportional to the number of distance calculations. Second, the number of distance calculations can be estimated through the skip ratio. After the distance calculation, Cubism compares the actual execution time with the expected value. If the actual execution time is longer than expected, Cubism determines that the warp balancing does not improve performance in current skip ratio. Therefore, Cubism sets the current skip ratio as the skip ratio threshold. Then, for subsequent iterations, Cubism performs the warp balancing only if the skip ratio is higher than this threshold. After the selective warp balancing, Cubism distributes the distance calculations between CPU and GPU. This figure shows an example of this task distribution. In this example, there are 4 tasks, each representing distance calculation. Cubism first distributes these tasks according to a predetermined task partitioning ratio. Since the GPU has a higher throughput than CPU, Cubism assigns more tasks on the GPU side. And after the distance calculation, Cubism adjusts this partitioning ratio based on the execution times of both processors so that both execution times become similar. This task distribution accelerates the k-means clustering by effectively using both processors. Now I present our evaluation results for Cubism. We conduct all experiments on the NVIDIA Jetson Orient platform, which is an embedded GPU with 8 SMs and a 12-core CPU. We compare Cubism with the prior GPU-based implementation of Inyan k-means clustering, which serves as a baseline. And we configure another technique called WB plus HETD to evaluate the effectiveness of our selective warp balancing technique. Unlike Cubism, this technique consistently applies the warp balancing and task distribution without considering the potential overhead of warp balancing technique. And we configure 9 data sets to examine the effects of various structures of real-world data sets. We select 3 numbers of data points and feature dimensions, then combining them to build the data set. And this graph shows the geometric mean of end-to-end speedup over the baseline. Cubism achieves a 23% performance improvement by improving the GPU thread efficiency and utilizing CPU and GPU effectively. To further analyze the performance, we conduct a case study for 3 individual iterations with varying skip ratios. In this graph, the x-axis shows the skip ratios and the y-axis shows speed up over the baseline. And if the skip ratio is close to 1, the warp balancing technique significantly improves the performance. However, if a skip ratio is 0, the warp balancing incurs a significant overhead while providing no performance improvement. As a result, WB plus HETD shows lower performance than the baseline. Cubism does not perform the warp balancing in such iterations, showing performance improvements in all cases. And so these results show the necessity and effectiveness of our selective warp balancing technique. Yeah, and we profile the hardware utilization during the clustering process for the baseline and Cubism. The table above shows the number of active threads per warp during the clustering. And Cubism achieves up to 3.3 times higher active thread than the baseline. And this achieving 9.1 active thread is a significant improvement considering the fundamental differences in the number of distance calculation assigned to each GPU. If a skip ratio is high, the variance of distance calculations for each thread increases. So even with our warp balancing, the thread with the most distance calculation becomes the critical path within a warp, making some thread remain inactive. So despite the warp balancing, the number of active threads is lower than 32. And the table below shows the average CPU utilization during the end-to-end clustering process. While baseline shows only a 10% CPU utilization, Cubism achieves a 77% CPU utilization. So these results highlight again our key message that efficient use of hardware resources is a key to improving performance. So in conclude, running K-means clustering on embedded systems faces two primary challenges. The skipping mechanism incurs a significant warp divergence, and existing algorithms do not utilize CPU for distance calculation. We propose cubism that improves both CPU and GPU utilization and accelerates K-means clustering on embedded systems. Yeah, so thank you for your attention, and I'd be happy to answer any question.
Thank you. Any questions, comments from the audience? Yes, please.
I have two quick questions. So for running the some portion of the program in the CPU, what kind of the code is running? It should not be CUDA.
Yeah, we implement the Inyan K-means clustering code in C and running in the host CPU.
How well optimized of the CPU-based code?
You mean the compiler optimization level, or?
No, in general, it is the general comment, general question.
Yeah, we think we implement the CPU code to utilize the most of CPU cores, and yeah, so I cannot capture the meaning of optimization exactly. Yeah.
Okay. Another question is how big is the portion of the workload to be executed in CPU?
So the question is the portion of K-means clustering distance calculations running on CPU.
Yes.
Yeah. Typically, we run the 20% of distance calculations in CPU. Yeah.
All right, let's thank our speaker again.
Thank you.
Yes, this one was the last session. Before, the closing remark, I like to thank all the speakers and audiences. Okay, he's already there. Youngjun Park is going to give a closing remark of LCTES 2025.
Okay, here comes pitch chair again. This is a really good sign because it means that this conference is almost done. Okay, so thank you for attending LCTES 2025. So we really thank all the authors, speakers, session chairs, reviewers, and attendees. So basically, I really appreciate your participation, including the great talks and the active discussions. And here are several this year's highlights. You might be boring, but it's also my job. Okay, so it becomes the 1.5 day conference now, and we invited two inspiring keynote talks, and we have really great talks from 16 full papers and 2 WIP papers, and also we had 7 successfully evaluated artifacts. Okay. Okay, and the last mission as the pitch chair of my side is the best paper award. Okay, so I need to select the best paper. So based on the average review scores, we had 2 best paper candidates. The first candidate is the modeling and verification of sigma delta neural networks using satisfiability modular theory. It's really long. Okay, which was presented yesterday. Okay, and also we have another best paper candidate with the really long titles, the advisor, the extensible dynamic binary instrumentation and analysis framework for open instruction set architectures, okay, which was presented today on the last session, okay, and based on the discussion of among the committee members who attended the conference without having any COIs, we finally select the best paper. So either with the first one, modeling and verification of sigma delta neural networks using satisfiability modulus theory. Is there the prepared? It should not be to me. It's not congratulations to me. So is there the presenter or also the paper here? It is surprise, and it is really normal. Do you know that after the presentation, the presenter becomes so tired and exhausted and disappears, okay? And they cannot be recovered until the conference finishes, okay? So that's normal, okay? So we can create some kind of the picture using the ChatGPT or something like that. But anyway, so many congratulations to the authors of this paper, okay? Okay, so we are pretty much done. So thank you again, and we'll see you at the next year LCTES, and please enjoy the remaining conference and enjoy the Seoul. Okay, thank you.